Hello everyone, Namaste. A very warm welcome to the National Science Day celebrations at LIGO India. राष्ट्रीय विज्ञान दिवस के अवसर पर लाइगो इंडिया टीम के तरफ से आप सभी का हार्दिक स्वागत है। आज हम आपके लिए लेकर आए हैं एक बहुत ही दिलचस्प कार्यक्रम। We have a very interesting lineup today on the occasion of National Science Day just for you. First, we have Coffee with a Scientist, where we will have conversation with two eminent researchers from the LIGO India scientific collaboration. So, as you all probably already know, the LIGO India project is a planned gravitational wave observatory as part of a global array of detectors along with LIGO in the US, Virgo in Europe, and Kagra in Japan. So the contribution of the project to the LIGO scientific collaboration will be through the LIGO India scientific collaboration. Many leading institutions in India form this LIGO India scientific collaboration, including several IITs, ICERs, Saha Institute of Nuclear Physics, Institute for Plasma Research, Tata Institute for Fundamental Research, Chennai Mathematical Institute, and many more. So today, on the occasion of the National Science Day, we are going to have a conversation with two eminent researchers from two institutions of the LIGO India scientific collaboration. So first we have Shashwat Kapadia from ICTS, who's going to talk about gravity through the eyes of Professor Einstein, a strange theory that actually works. Over to you, Shashwat.
Okay. Hello, everyone. My name is Shashwat Kapadia. I am a postdoc at ICTS, as well as a member of the LIGO Virgo Kagra collaboration, as well as the member of the LIGO India collaboration. And today I'm going to talk to you about Einstein's general theory of relativity, which is just a fancy name for his theory of gravity. And I have titled my talk, Gravity Through the Eyes of Professor Einstein, a strange theory that actually works. Now, my hope is that by the end of this presentation, I would have convinced you that this theory is not only strange and beautiful and elegant, but it is also a theory that makes testable predictions. And in fact, a number of spectacular tests have been conducted on Einstein's theory of general relativity. And all these tests, Einstein's theory of gravity has passed with spectacular colors. All right, so before I actually jump into the presentation proper, I thought that I would do a little digression. So the reason I decided to put this in is because I thought that in an interesting way, it actually connects to the whole idea, to the core of Einstein's theory of general relativity. And so this is a little incident that happened when I was about 13 or 14 years old. My physics professor was very fond of Tibetan Buddhism. And in Tibetan Buddhism, you have this very beautiful artifact, which is known as the endless knot. So it's basically a string which is tied up in a very intricate way. And my professor, my school teacher, he told me, or rather he asked me a question, what do you think this is? What is the knot? Now, of course, at the time, I didn't really realize what he was asking, because I didn't really realize he was asking me a philosophical question, and I just gave him the answer, well, the knot is the knot. What's there more to it? So then he asked me to think a little bit more carefully. And he said that if you look at this endless knot, it seems to have a separate identity. But at its core, the knot really is just the string. It's a distorted version of the string. It's a warped version of the string. But ultimately, this very intricate knot is just the string. Now, I'd like you to keep this little anecdote at the back of your heads. And right at the end of the presentation, I will get back to this anecdote and hopefully you will find why this anecdote is pertinent to this presentation. All right, so now I jump into the presentation proper. So like I said, I will be talking to you about Einstein's theory of gravity, and I will do so in three parts. The first part talks about gravity before Einstein. So this is basically to give you a historical context. I will then follow it by Einstein's theory proper, where I'll describe to you what the theory is all about, and also hopefully convey to you the thinking, the thought process that Einstein actually went through as he came up with his theory of gravity. And I will then come to the third part, which will talk about a few of its predictions. But even though there are like a number of predictions that Einstein's theory of gravity makes, I will only talk about 3 or 4, and I will especially focus on a prediction which says that very massive objects that accelerate produce gravitational waves. And I will also talk about how we can detect these gravitational waves and how there is a very exciting project which is currently underway called LIGO-India. So I will talk to you a little bit about that as well. All right, so like I said, what we're trying to do here, what Einstein's theory of gravity tries to do is essentially, it tries to answer the question, what exactly is gravity? Now, of course, Einstein was not the first person to ask this question. This is a question that was asked for millennia, actually. Now, the reason this question is particularly relevant to us is because gravity is something that we experience every day. It's the reason why we don't just float off into space. However, understanding the mechanism by which gravity actually works has proved to be difficult even for the greatest of minds that have walked on this earth. Now, there is a very interesting thing about gravity that's quite easy to miss, and that is that gravity seems to be fairly ubiquitous. It really doesn't care about the objects on which it is acting, regardless of the nature of the object, regardless of its color, its shape, its chemical composition. All objects tend to fall towards the ground. Apples, for example, tend to fall towards the ground. Raindrops, which are very different from apples, also fall towards the ground. A tennis ball, if it is launched in the air, it will eventually fall towards the ground. And in fact, conscious sentient human beings, if we were to toss ourselves into the air, we would also eventually fall to the ground. Now, all these things are very different in shape, in color, in chemical composition, and yet under the influence of gravity, they seem to behave in exactly the same way. Now, this astute observation was made by the great Greek philosopher way back in 330 BCE. And what he essentially stated was that all objects have a natural tendency to move towards the center of the earth, which he called their natural place. Now, the problem with this theory of gravity is that while it is an astute observation, it is not very good at being predictive. It cannot make very accurate predictions. For example, if I were to throw a ball at a certain angle, Aristotle's theory of gravity cannot predict that it will follow a parabolic path. So many years later, the great British physicist, Sir Isaac Newton, came up with arguably one of the greatest theories in theoretical physics when he put forward his theory of gravity in 1687 CE. Now, Newton's theory of gravity was very different from Aristotle's theory of gravity. What Newton essentially stated was that gravity is a force. Now, this force is not just a property of the earth. So it's not just that objects have a natural tendency to go towards the center of the earth. Rather, gravity is a universal property of matter itself. So any object that has mass will exert a force of gravity on any other object that has mass. So then he put forward his very famous equation. Now, without worrying about the maths, I will just describe to you what this equation says. All this equation says is that the force of gravity is proportional to the masses of the objects and inversely proportional to the square of the distance that separates them. So in other words, if you double the mass of either of the objects, the force of gravity doubles. On the other hand, if you double the distance that separates these objects, the force of gravity reduces by a factor of 4. Now, this was a truly remarkable theory because not only was it able to explain motion of objects near the surface of the Earth. For example, it could explain why apples fall towards the ground and also predict at what rate apples will fall towards the ground. But it was also able to explain the motion of celestial objects. For example, planets orbiting the sun, their exact trajectory was predicted by Newton's theory of gravity. In fact, this theory of gravity is so powerful that even our own even our own satellite missions, or missions that try to explore other worlds, such as ISRO's Chandrayaan missions, needed only to use Newton's theory of gravity to be able to plot its trajectory as it explored the moon. So in spite of its spectacular success at predicting things, there was a very big conceptual issue in Newton's theory of gravity that, in fact, Newton himself knew. So I'm just going to read out a quote here. So what he says here is that it is inconceivable that inanimate brute matter should, without the mediation of something else, which is not material, operate and affect other matter without mutual contact. So to kind of put it in somewhat simpler terms, what Newton is saying here is that he doesn't really know how gravity acts. How is it that the Earth and the moon that are separated by such a great distance are still able to exert forces of gravity on each other? How is it that the Earth is able to go all the way out to the moon and somehow hold it in its orbit around the Earth? Now, this is something that Newton didn't really understand. All he came up with was a theory of gravity. He came up with an equation, but he could not actually tell how gravity exactly works. And it took many centuries later for Albert Einstein to come and to finally actually answer the question, what exactly is the mechanism by which gravity works? And he did so in 1915. Now, Einstein was particularly interested in observing objects near the surface of the Earth. And this is something, of course, that was known much before Einstein as well. Nevertheless, according to the existing theory, Newton's theory of gravity, it was postulated that all objects will fall towards the ground at exactly the same rate, regardless of their mass. Now, of course, it may seem a little bit counterintuitive because we don't necessarily see that every day. For example, if you were to take a bowling ball and a feather like you have here on this picture, if you were to release it from the same height, obviously the bowling ball is going to fall faster towards the Earth than the feather. However, there has been a spectacular experiment that was done where these two objects were kept in a depressurized chamber and all the air was removed so that the air no longer affects the motion of these objects. And then when this experiment was conducted, when both these objects were released from rest, notice how they exactly fall towards the ground at exactly the same rate. This is truly a remarkable video and a remarkable experiment that demonstrates that all objects fall towards the ground at exactly the same rate. So I'm going to let this video go all the way through to the end. And you will see that both objects are falling at exactly the same acceleration towards the ground. All right, now, like I mentioned, this fact was actually known before Einstein. In fact, Newton had his own version of explaining this. So what Newton essentially said was that when you have a heavier object, like the bowling ball, the force of gravity on the bowling ball will be stronger. However, because the bowling ball is more massive, it will also have a larger inertia. It will have a larger resistance to motion. On the other hand, a feather is lighter than the bowling ball, and therefore the force of gravity on the feather will be weaker. But on the other hand, because it is lighter, its inertia is also going to be smaller. And what Newton said was that these two effects, the stronger pull versus larger inertia, as opposed to weaker pull versus smaller inertia, these two effects perfectly cancel each other so that both objects fall towards the ground at exactly the same rate of 9.8 meters per second. Now, Einstein wasn't very happy with this explanation. He thought that this perfect cancellation seemed a little too much of a coincidence. He wanted something more fundamental for his theory of gravity. And it turns out that Einstein was working in his office as a patent clerk. And one day he had a vision, if you like, what he called his happiest thought. Now, I'm going to let you guys decide whether this is a happy thought or not. But nevertheless, this is what he came up with. So what he imagined was that supposing he were to go inside an elevator, okay, I'm going to run the animation here. So supposing he were to go inside the elevator and the elevator, is going up, and suddenly Einstein realizes that the elevator is no longer working. And sure enough, as you will see, after a point in time, the rope that is holding the elevator is going to snap. And when Einstein realizes that, initially, I guess he's a little bit scared, and the rope snaps and the elevator is in free fall. Now, of course, if the elevator is in free fall, so is Einstein and everything connected to Einstein, as well as his belongings. Now, here's the important fact. Because all objects fall towards the ground at exactly the same rate, the elevator falls towards the ground at 9.8 meters per second per second. Einstein falls towards the ground at 9.8 meters per second, as well as his belongings also fall at the same rate. Now, because of that, you can imagine that the floor of the elevator and Einstein's legs are both falling towards the ground at exactly the same rate. So effectively, the floor of the elevator is no longer pushing back on Einstein's feet. Effectively, Einstein is floating. Now, what Einstein said was that, well, supposing I was completely oblivious to what's happening outside, and supposing I were in free fall in such an elevator, because I would be floating around, it's effectively as if gravity has been switched off. There is no way for me to do an experiment that will tell me that I am in fact in free fall rather than somewhere outside in outer space. Now, this is what Einstein considered to be his happiest thought. So in shorter terms, the idea here is that if objects are in free fall, effectively, gravity has been switched off. Now, this is not just a fancy idea that Einstein came up with. This is, in fact, a technique that astronauts use in order to be able to train when they go on their missions in outer space. And I have here a video of what is called a zero gravity plane. So what a zero gravity plane does is basically it goes up way up high, as you see on the left-hand side panel. And then when it goes up way up high for a few seconds, it actually then stops flying up and goes into free fall. Now notice in this video, as the airplane goes into free fall, the astronauts inside the airplane are effectively without gravity. It appears as if gravity has been switched off. So I'm going to play the video. So as you can see, as the plane has been the astronauts have been upwards, effectively as if gravity has been stopped. Does seem to switch off gravity. All right, so now I guess one could ask the question, if by free fall one can switch off gravity, is there a way by which we can switch on gravity? And the answer, it turns out, is yes, if you think of this following thought experiment. Now, supposing you had the same elevator that Einstein imagined, but instead of it being in free fall, imagine that it is somewhere far away from all gravitating sources in outer space. And supposing you were to attach a booster at the bottom of the elevator, and suppose then the elevator were to start accelerating upwards. Now, as the elevator accelerates upwards, this person who is inside the elevator will release the ball, and to the person in the elevator, it would seem to him or her that the ball is actually accelerating towards towards the floor of the elevator at exactly the rate at which the elevator is accelerating upwards. And in fact, no matter where you place the object inside the elevator, when you release that object, because the elevator is accelerating upwards, it would seem to the person inside the elevator that the ball is accelerating towards the floor of the elevator at exactly the rate at which the elevator is accelerating upwards. Now consider then this following situation. Suppose now you have two observers in two different elevators, one which is in outer space like the one that we had in the previous slide, and another one that's near the surface of the Earth. Now, if the elevator that is in outer space is accelerating upwards at exactly 9.81 meter per second, then the person inside the elevator will not be able to tell whether he's in fact in outer space and the elevator is accelerating upwards, which is what is causing the ball to fall towards the ground at 9.8 meter per second. So he's not going to be able to tell that, or that whether he is near the surface of the Earth and in fact static, and the ball is falling towards the ground at 9.8 meter per second due to the force of gravity caused by the Earth. So what you notice here is something that is referred to as the equivalence principle. And the statement of the equivalence principle is very simple. You can always switch on gravity by moving to a frame that is accelerating. So if you want to have gravity or you want to feel the effects of gravity, just like you do on the Earth, you can also do that by going to an elevator that's accelerating upwards in outer space at exactly 9.81 meters per second. So this is the analogy. And in fact, Einstein was very, very fond of this equivalence principle. And he said that nothing that the person who is in outer space, there's nothing that this person can do, no kind of experiment that will be able to tell him that the reason the ball is falling towards the ground at 9.8 meters per second is due to acceleration and not due to gravity. So then Einstein thought that, well, let's push this analogy a little further. What if, supposing in this elevator in outer space, he has this torch and he shoots light from this torch, and the elevator is accelerating upwards. And because of that, of course, since the floor is catching up with the light beam, to the person inside the elevator, it would seem as if the light beam is curving. Now, remember, Einstein was very fond of this analogy. So he said that whatever happens in this accelerating elevator should also happen in an elevator on the surface of the Earth that is not accelerating. So the question then is that supposing someone were to shoot a beam of light near the surface of the Earth within an elevator that is not moving, should it actually bend or not? Now, at the time when Einstein thought of this idea, it was not at all clear whether the force of gravity could in fact act on light, because light, it turns out, it doesn't have mass. And remember, Newton's theory of gravity says that in order for the force of gravity to act, objects need to have mass. So then essentially what Einstein said is that, no, I would rather stick with my analogy and say that the light must bend. Now, of course, if the light must bend near the surface of the Earth, then Newton's theory of gravity cannot be correct. So what he thought then was perhaps another way to think of gravity is not as a force that pulls on massive objects, but rather that the space through which this beam of light is traveling is itself curved. So another way to think about gravity is to think of it like, if supposing you have a massive object, then it would curve space around it, and any other, say, smaller object in the vicinity of this massive object, the trajectory of the smaller object would be completely determined by the geometry of space around the massive object. So now the moon goes around the Earth, not because there's a force of gravity acting from the Earth on the moon, but rather because the Earth curves the fabric of space and the moon is compelled to go around the Earth because of the curvature of space around the Earth. So an interesting analogy that is often given is that of a massive object, say on a trampoline. And if you were to then launch a few lighter objects on this trampoline, then the trajectory of these objects would be governed by the curvature. So let me just play the video here. So you have the massive object at the center. And as you can see, the trajectory of the marble is completely determined by the curvature of the trampoline caused by the massive object at the center. In much the same way, the trajectories of astrophysical objects, such as the moon around the Earth or the Earth around the sun, these trajectories are determined by the curvature of space around the sun, or in the case of the moon on the Earth, by the curvature of space around the Earth. All right, so now what about objects near the surface of the Earth? Well, rather than thinking about them as being caused by the force of gravity, these trajectories are in fact determined by the curvature of space caused by the Earth itself. So basketball, for example, when it is launched in the air, it follows this parabolic trajectory, not because of a force of gravity, but rather because the nature of space itself in the vicinity of the Earth is curved. And in fact, this curved trajectory is completely independent of mass. Even if a more massive object, say a car, if a car were launched into the air, it would also follow a curved trajectory, again, not due to the force of gravity, but rather because the nature of space itself around the Earth is curved. All right, so this is a very interesting theory, but in order for it to be a scientific theory, it has to be tested by experiments. And one of the first experiments to actually demonstrate that Einstein's theory of gravity is correct is a phenomenon called gravitational lensing. So the idea here is that the sun, because of its mass, causes a curvature in space, and light from a star is bent in the vicinity of the sun and reaches the Earth because of the curvature around the sun. Now, because we follow straight line trajectories, the location of the image of the star will be different from the true location of the star. Now, astronomers, when they actually did this experiment, they knew the true location. They measured the position of the image, and they found that the amount of deviation is exactly what was predicted by Einstein's theory of gravity. And this experiment was in fact conducted very soon after Einstein proposed his theory. It was done in 1919. So this was one of the first confirmations that Einstein's theory of gravity, even though it sounds very strange, curvature of space and all, it actually seems to work. Another very interesting proof of Einstein's theory of gravity is the trajectory of Mercury. Now, it was known much before Einstein that Mercury's trajectory, or Mercury's orbit rather, doesn't quite close on itself. It traces out this flower-like shape as it goes around the sun. Now, this was known, like I said, this was measured by astronomers much before Einstein. And people tried to actually explain why Mercury's orbit doesn't quite close on itself. And using Newton's theory of gravity, it was found that only a part of this motion of Mercury was explained in more numerical terms. The rate at which Mercury precesses, meaning the axis of the orbit of Mercury is gradually changing directions, and the rate at which this is happening is approximately 5,557 arc seconds per century, where an arc second is 1/3600th of a degree. So it's a very tiny amount. The precession is very gradual, but nevertheless, it is there. And according to Newton's theory of gravity, if you were to take the effects of the other planets, you would in fact predict precession of the order of 5,557 arc seconds per century. Nevertheless, the amount that was measured by astronomers was not that number, but was rather 5,600 arc seconds per century. There was a missing piece of 43 arc seconds per century. And this is where Einstein stepped in and decided to see, well, whether his theory of gravity could in fact account for this missing piece in the precession. And in fact, when he did that, he got an answer of 43 arc seconds per century. So I actually forgot to mention here that one of the postulates using Newton's theory of gravity was that there was a hidden planet near the sun that was causing this missing piece. Astronomers named it Vulcan, and in fact, Vulcan was never found. So in conjunction with the fact that Vulcan was never found and Einstein's general relativity predicted the missing 43 arc seconds per century, this was further confirmation that what Einstein had was in fact correct. All right, now we kind of move into some of the more exotic predictions of Einstein's theory of gravity, and that concerns stars. Now, we know that stars basically burn nuclear fuel for a very long period of time, for billions of years sometimes. Now, the way the stars remain stable is by the combination of two processes. The nuclear fuel that is burning at the core of stars is trying to blow the star apart. On the other hand, because stars are so massive, the star is always trying to collapse in on itself. So the combination of the two, the nuclear forces trying to blow the star apart and gravity trying to crush it, the combination of the two maintains a very nice balance for several billions of years. Nevertheless, eventually the nuclear fuel runs out and the star basically collapses in on itself. It collapses in on itself because of its own weight. And sometimes, if the star is sufficiently massive, the resulting collapse causes one of the most spectacular explosions in the universe, known as a supernova. And again, depending on the mass of the star, this supernova can leave behind a very interesting and very strange object known as a black hole. Now, a black hole is basically an object. We don't know exactly what is right at its center, but according to Einstein's theory of gravity, there is a singularity at the center of infinite density. And around the singularity, you have something known as the event horizon. And it turns out that anything that lies beyond the event horizon cannot escape the black hole. Not even light, if it lies beyond the event horizon, can escape the black hole. In fact, that is why the black hole got its name. That is why black holes are, well, black, because not even light can escape from black holes if the light starts out beyond the event horizon. Now, interestingly, it turns out that in nature, we find combinations of black holes, what are called black hole binaries. And these binaries, just like objects in our solar system, orbit each other. But nevertheless, because they are so massive, they do something that is additional and quite different from what planets do. Over a period of time, black holes gradually come closer and closer to each other. They spiral in or in spiral, and they eventually merge. Now, this is quite different from what we observe of planets going around the sun. The planets pretty much stick to their own trajectories. Nevertheless, black holes that are initially set in orbit around each other over a period of time come closer and closer and closer until they merge. And the reason they do that is, again, one of Einstein's spectacular predictions. It is because of the emissions of what is called gravitational waves. Now, what is a gravitational wave? I guess the easiest way to think of gravitational waves is to imagine ducks in a pond. Now, when you have ducks in a pond that are moving, they produce ripples in the fabric of the water, if I were to put it that way. In much the same way, if you have massive objects that are accelerating through space, and black holes orbiting are in fact accelerating, then they would also produce ripples in the very fabric of space. So these gravitational waves effectively carry away the energy of the orbit and the angular momentum of the orbit. And because they do that, these black holes come closer and closer to each other, they in-spiral, and eventually they merge. Now, again, this is a very fancy prediction of Einstein's theory of gravity, but the question is, can we actually detect them? And it turns out that the answer is yes. And there was a spectacular detection that was done about, I'd say now about 6 years ago. So the way that gravitational waves were detected were using a method called interferometry. Because of lack of time, I won't go into details of how interferometry actually works. But the rough idea is that when gravitational waves interact with an elongated object, they will stretch and squeeze the object. And using interferometry, and say you have sufficiently long arms, you can then conduct experiments to measure this stretching and squeezing of the arms. So that is what these two detectors here were able to do 6 years ago, and detect the very first gravitational waves. There is one detector in LIGO Livingston, or rather in Livingston in the United States, and the detector is called LIGO, which is short for Laser Interferometer Gravitational Wave Observatory. There's another detector, again in the United States, in Hanford. And these two detectors were the first to detect gravitational waves that were produced by a merging binary black hole of masses about 30 solar masses. So each object in this binary was about 30 times the mass of the sun. Now, since then, very many detections of binary black holes merging have been made through the detection of gravitational waves. What I have here is a video of some of the detections that were made during the first and second observing runs of the LIGO detectors. And in fact, I should mention here that during these observing runs, somewhere in the middle, an additional detector also became operational in Europe. So some of these detections were also made by all three detectors together. Now, one of the things that I want to point out in this video is that these gravitational waves don't all have the same shape. Depending on the masses of the black holes, the shape of the gravitational waves will be different. Now, this is, of course, a very nice thing. What this is effectively telling you is that the masses of the objects are imprinting themselves on the shape of the gravitational waves. So if we were to work backwards, if we detect a gravitational wave and we figure out what their shape is, we should be able to infer properties about the objects that produce them. So one of the first things that one can do by just detecting gravitational waves is to be able to detect, or to be able to infer, the masses of these black holes. Now, of course, gravitational waves are not just produced by black holes. Like I mentioned, any sufficiently massive object that accelerates will produce gravitational waves. Now, there are other very exotic objects called neutron stars that can also produce gravitational waves when they accelerate through space. A neutron star is essentially a very, very dense star consisting essentially of neutrons. In fact, if memory serves, a teaspoon worth of neutron star material is worth several hundreds of thousands of super tankers. So that just gives you an idea of how incredibly dense these objects are. So in 2017, in August, the very first binary neutron star merger was detected, and arguably this event was even more spectacular than the very first detection of gravitational waves. And the reason for that is not only did this event produce gravitational waves, but it also produced light in a whole range of frequencies. And therefore, this event enabled one of the most comprehensive follow-up efforts ever in the history of humankind, actually. So you had a number of telescopes that were observing this event at the same time. You had, of course, the gravitational wave detectors, the three that I mentioned, two in the United States, one in Europe. And once the gravitational waves were detected, this message was sent out to the telescopes all over the world. And these telescopes observed the light that was emitted by the merger of this binary neutron star. And the scientific riches that were obtained because of this joint detection between gravitational wave observatories and electromagnetic telescopes, that is, telescopes that observe light, because of that, a number of very interesting things were inferred. We now have a much better understanding of how matter at these extreme densities works. We now know, very interestingly, that some of the heavier elements of the periodic table were in fact synthesized during the merger of neutron stars. So just to a little bit of a digression, the gold that you probably have in your ornaments were produced most likely in the merger of neutron stars. So this is something to contemplate over, right? And the next time you wear a gold ring or a gold necklace, just imagine that this thing that you're wearing was produced during the merger of neutron stars many, many years ago, millions to billions of years ago. A number of other interesting scientific facts were inferred from the merger of binary neutron stars. I don't have time to go over all these details, but if you're interested, I would strongly recommend that you look at Professor Varun Bhalerao's lecture. Is going to happen sometime later in the day today, and he's going to talk to you a lot more about the merger of this binary neutron star and what are the amazing things that you can actually discover because of the joint observation of gravitational waves as well as electromagnetic telescopes. Now, the reason that one could actually do this kind of joint observation is because the source that produced these gravitational waves, these binary neutron stars, were very well localized in the sky. So to break down to you the sequence of events, the gravitational waves were first detected by the gravitational wave telescopes, two in the United States, one in Virgo. Now, using this information, using this gravitational wave data, we were able to determine where the source is located in the sky. This information is then passed to the electromagnetic telescopes. These are the telescopes that observe light, basically. And these telescopes then have to slew to the location where the gravitational wave observatories think that the merger happened, and then start observing and seeing whether there is in fact an electromagnetic counterpart, whether light was in fact produced during the merger of this event. Now remember that depending on the number of telescopes, rather depending on the number of gravitational wave observatories you have, the localization area within which the source merged becomes smaller and smaller. So if you increase the number of detectors, the sky area over which the electromagnetic telescopes have to scan in order to catch the electromagnetic counterpart becomes smaller. Now, like I mentioned, this event, this binary neutron star merger, was only observed by 3 gravitational wave detectors. So it had a limited sort of ability to localize the source. Nevertheless, if supposing an additional detector were to be built in India, then the localization area corresponding to this event would shrink by a factor of 3. So what I have here in this image are a set of detectors that are currently built. There was a plan to build a LIGO-India detector. That plan has now been approved. So this is a very exciting time for us. So basically there will be an additional detector to be built in India. And the effect of this detector can be seen very clearly on the slide. So this is again the same event that I talked to you earlier about. This is the merger of the binary neutron star. When you just have the LIGO detectors and the Virgo detector, which is what you had when that merger was detected, the electromagnetic telescopes had to scan a much larger sky area to see if there is an event that happened within that area. However, if LIGO-India had existed at that time, the sky area that would have been scanned would have been reduced by a factor of 3. So what does that mean in terms of observation? What that means is that the electromagnetic counterpart would have been caught faster. And because it would have been caught faster, we would have been able to see a lot more of the merger of the event itself, very close to when the two neutron stars in the binary collide. So a lot more can be learned just by the addition of a detector. And therefore, we are very excited as gravitational wave observers that there will be an additional gravitational wave detector that will be built in India. All right. So this, just to belabor the point a little bit more, Binary neutron stars are not the only sources of gravitational waves that can also produce light. You can also have kind of a mixed bag sort of situation where you have one neutron star and one black hole. And as the neutron star gets closer to the black hole basically tears apart the neutron star, and that produces a lot of light. So in principle, even the merger of a neutron star with a black hole could produce light or electromagnetic waves. And if supposing we had a LIGO-India detector, then it would considerably improve our ability to localize the source, and the electromagnetic telescopes would then have to scan a much smaller sky area in order to catch these electromagnetic waves. So here I have an example of how LIGO-India would have really helped. So in the third observing run of the LIGO Virgo detectors, there were two neutron star black hole systems that were detected through gravitational waves. Nevertheless, no electromagnetic counterpart was detected. Now, we don't know whether these sources did produce an electromagnetic counterpart or not, but if they did produce a counterpart, potentially one reason we did not actually catch it is because the sky area that the source was localized to was extremely large. So that's what you see on the left hand, the top and bottom left-hand side panels. However, if LIGO India were present, then what we would have had was a much, much smaller localization sky area. This would have then enabled electromagnetic telescopes to scan a much smaller area and potentially catch any electromagnetic counterpart if it were produced. So again, hopefully I have convinced you that a detector like LIGO India would cause considerable benefits to the scientific and astronomical community, because it would enable a joint detection of gravitational waves with electromagnetic waves. All right, so I basically now come to the end of my talk. So I'm going to summarize here that Einstein's theory of gravity, apart from being a very elegant and beautiful theory of gravity, has also predicted a number of spectacular things, and these predictions have been tested. These include gravitational lensing, like I talked about, the precession of Mercury. One topic that I was unable to get to was the expanding universe, but this is again a spectacular prediction of Einstein's theory of gravity. And the part that I focused most about, which is also a prediction of Einstein's theory of gravity, is that massive accelerating objects, such as binary black holes or binary neutron stars, produce gravitational waves. Now, these gravitational waves have essentially opened a new window to the universe, or if you want to put it in another way, it has opened a new branch of astronomy itself, where we have a way by which we can understand exotic objects such as black holes and neutron stars. And the hope is that with the construction of LIGO India, which will hopefully happen within this decade, the localization reduction will enable some of the most spectacular detections, joint detections, that we have yet seen. And of course, Einstein's theory of gravity has a lot more than what I have talked to you in this presentation. And my hope is that if this talk was interesting to you, then you will actually take the trouble to look up books or videos. There are a lot of interesting documentaries on Einstein's theory of gravity, as well as gravitational waves and LIGO India. So I would strongly urge you to explore these. And for now, if you have any questions, I would be happy to answer them. Thank you very much for your attention. All right. So in fact, I think I thanked you a little too soon. I forgot about the digression that I made right in the beginning. Now, there's a reason why I made that digression, and hopefully it will tie everything together, pun fully intended. So the idea here is that just like the eternity knot, right? My physics teacher asked me, what is the knot? And the answer to that question was, the knot basically is the string. Now, apply this to Einstein's theory of gravity, and hopefully you will realize how weird this is. What Einstein essentially says is that gravity is the curvature of space. So essentially what Einstein is telling us, that gravity literally is just space. It's a distorted version of space. It's a warped version of space, but ultimately gravity is really just space. And as weird as this sounds, like I have hopefully demonstrated to you, Einstein's theory of gravity actually works. It is indeed a strange theory that works. Okay, now I should probably thank you, and I'm happy to take any questions. At the chat right now to see if there are questions, and I do see that there are a few questions. So I'll just go in order as per what I see on the chat. So the first question is a very good question. Can quantum nature of gravity be detectable with gravitational waves? So the answer to that question is that yes. So the answer to that is yes. In principle, the quantum nature of gravity might be detectable. This is something that is still an ongoing sort of enterprise where we look at the shapes of gravitational waves to see if there are any modifications with respect to Einstein's theory of gravity. As of now, we have not observed any obvious deviations from Einstein's theory of gravity, but that doesn't mean that we will not in the future. So the search for deviations from Einstein's theory of gravity, such as the quantum nature of gravity, might reveal itself maybe sometime in the future. So this is a great question. Okay, so I will now go to the next question, which says, what would be the prospect of neutrinos with gravitational waves, since both of them are great cosmic messengers which can travel far in cosmos undisturbed? Is there any joint search going on? Again, a nice question. The answer to the second part is that no, currently there is no search going on because the detectors are not operational. They will hopefully be operational in several months' time. However, at the moment, they're not operational, so there are no current joint searches going on. However, like I mentioned during my talk, that there were 3 observing runs that were conducted, and in the second and third observing runs, there were also these follow-up efforts, including following up other messengers such as neutrinos. So hopefully when the next observing run, which is the 4th observing run happens, there will be joint detections, and maybe some of those joint detections will also include neutrinos. All right, so the question after that is, how big a role will there be for data scientists? Okay, this is again a very good question. So I guess I could answer this question in 2 parts. There's of course the principle of data science, which goes heavily into the analysis of gravitational wave detection. On the other hand, uh, the second part to this answer is that the data is also made publicly available after a period of time. In fact, the data from the first and second observing runs, and I believe at least a part of the third observing run, the data is actually available. So then people outside of the LIGO, Virgo, Kagra community can also analyze this data to see if they can find anything. I mean, I don't know personally, but I would not be surprised if there are data scientists who are also trying to see if there are any gravitational waves that they can find in the publicly available data. Okay, so next question, how can I build a good profile enough to apply for such data science roles in LIGO India? So I guess I could. I'm very glad that you're interested in gravitational wave science and gravitational wave data analysis. What I would recommend is that you look at the LIGO India website. And there you will find some contact information that you can reach out to, and I'm sure that the people will be happy to respond to your this specific question. So please feel free to definitely reach out to the LIGO India community. The contact information should be available on the website. All right, next question. Is it possible to detect gravitational waves from sources outside our observable universe? I guess the short answer to that question is no, because I think there is a fundamental limit out to which you can actually see the universe. It's called the horizon. So anything that lies beyond this horizon will forever be undetectable to us. It's basically a consequence of a consequence of two things. One is that the universe is not only expanding, but it's also accelerating, meaning that the further away the sources are, the faster they are moving away from us. Now that combined with the fact that gravitational waves travel at the speed of light means that there will be regions of the universe that are moving away too fast for even light to reach us in time. So the answer to your question is no. Anything that lies beyond the observable universe will never be detected, unfortunately. Okay, so I guess I can wait maybe for a few seconds to see if there are any additional questions. All right, so I don't see any additional questions. So I would like to thank all of you for your attention and for actually showing up for this presentation. I hope you enjoyed it, and I hope this has like stirred your curiosity to learn more about Einstein's theory of gravity, gravitational waves, as well as LIGO India. Thank you very much.
For this excellent presentation, and also to all of you for asking all these interesting questions. Next, in Coffee with the Scientist, we have an LISC focus session. We have with us Apratim Ganguly. Apratim is gravitational wave data scientist at the Inter-University Center for Astronomy and Astrophysics at Pune. And he's going to tell us about a gravitational wave peak at the stellar graveyard. Over to you, Apratim.
Hello and good morning, everyone. I'm Apratim, and I'm a gravitational wave data scientist in the LIGO-India group at IUCAA, and also a member of the LIGO-Virgo collaboration from March 2019. So I joined the collaboration after the first and the second observation runs. Shashwat, in his presentation, did talk about the basics of GR, gravitational waves, and also some highlights of the first and the second observation runs, while I will be talking about the latest one, which is the third observation run, and the current status. Just a disclaimer before I start my talk, I'm going to assume that you already know what gravitational waves are. That is, their ripples in the fabric of the space-time. You already know what LIGO and the Virgo detectors do. That is, they detect gravitational waves from violent cataclysmic astrophysical events like mergers of black holes and neutron stars. With that, and also I just want to let you know that the poster in the background shows all the gravitational wave mergers detected to date by the LIGO and the Virgo detectors. So I've intentionally darkened it a bit, since the primary goal of this talk is to unfold this slowly to you, the different features of the confident detection. Okay, with that, we move on to the next slide, where I give you a super quick recap of the first two observing runs of the collaboration. The advanced detectors came online in September 2015 and underwent the first observing run, O1, which lasted up to Jan 2016. The only operating detectors were the two LIGO detectors at Hanford and Livingston, and the double coincident operation time was for about 49 days. After that, there was a long enough commissioning break for various upgrades of the detectors to increase the sensitivity and hence our reach to detect gravitational wave events. It started up for operations back for operation for the end of 2016 and continued till August 2017. The double coincident observations of the LIGO detectors happened for 118 days. Virgo detector in Italy joined in August 2017 for a triple coincident uh, observation time of around 15 days. And as you know, many exciting observations happened during this runs, as Shashwat has already mentioned. But just to recap, there are like 10 binary black holes and one binary sun observed, and this is part of the gravitational wave transit catalog 1. And you can see the plot here. Basically, it shows the LIGO and the Virgo have discovered a new population of black holes, which are shown in blue, with masses that are larger, much heavier than what had been detected with X-ray observations, which are shown in purple. So also you can see the neutron stars observed in the electromagnetic regime in yellow, and GW170817, which is the only binary neutron star observed in the first two observation run. Okay. After the second observation run, the detectors were off for quite a long time, for significant commissioning break and significant upgrades to the detector, particularly the implementation of the frequency dependent squeezing, which significantly improved the detector sensitivity. And we came back online in April 2019. The third observing run had a small break in between the two halves, and that is why it is called the O3A and the O3B. We accumulated a triple coincidence time in the first 7 months of about 81 days, and a triple coincidence of 75 days in the second half, which was cut short because of the pandemic. So here, the first and the second and the third, first half of the third observing run is part of gravitational wave transit catalog 2. But when you add the second half of the third observation run, it becomes gravitational wave transit catalog 3. And you can see an analogous plot of what you saw in the previous slide here, where you see the LIGO and the Virgo detections, the binary black hole detections in blue, red are the electromagnetic black hole detections, yellow are again the neutron star detections, and then you see the binary neutron stars and the neutron star black holes here. So the only thing that you can take away from this plot is we have numerous detections now. Okay, this plot here shows the cumulative number of detections versus days in each run period, like O1, O2, O3A, O3B. So we have now a total of 90 confident events, and all of these are consistent with gravitational waves from compact binary mergers. By compact binary mergers, I mean binaries of black holes, neutron stars, or mixed binaries of black holes and neutron stars. This is in the range of stellar masses, so a few times the mass of the sun to a few hundred times the mass of the sun. More massive objects will emit gravitational waves and frequencies which are too low to be observed by the ground-based detectors. So here you can see a nice increase in the number of events, detected number of events, which is correlated to the dramatic improvement of the detector sensitivity. Okay, so in the next couple of slides, or the couple of videos, which will show merger animations, all detected events by LIGO and Virgo detectors. You can see the detected binaries and a vast range, as can be seen from the sizes of the black holes, which are denoted by circles in white. The blue dots here are the neutron stars. So you can see a bi-neutron star, neutron star, black hole, binary. Right. So this video is basically the first, second, and the first or third observing runs. While if I go to the next video, it shows all the merger animation of the second half of the third observing run. Right. Moving on to the next slide. As I mentioned before about the detector upgrades over the various observing runs, this plot show how to measure the improvements in detector sensitivity. So here you can see the BNS, the binary neutral star range, as a function of time for different observing runs that have increased dramatically. It tells you how far the detectors can see binary neutral stars with confidence. So it is around, say, 100 megaparsec for the Livingston detector by the end of O2, which increased to 140 or even higher in O3A and O3B respectively. Similar improvements can also be seen for, say, the other detectors. Now, you know that having a wider reach basically allows you to observe many more interesting events. Okay, so in the next few slides, I will talk about a few significant detections that happened during O3. And first up, I will be talking about GW190412, which came quite early in the third observing run. So I'm guessing you already know about the nomenclature. So this was observed on 12th of April 2019. Now, what's so interesting about this is this was the first clear detection of a black hole signal that had an unequal mass ratio. So up to this point, the observations were consistent with equal mass black holes. But here was the first clear signature, as you can see from the mass ratio distribution, defined as the ratio of the lighter to the heavier component of the binary, that this is an asymmetric binary. So if it was equal mass, the mass ratio would have been equal to 1, but now you see the mass ratio is much smaller. It's 0.3. Okay, now the video you see is basically the numerical simulation of two black holes that in spiral and merge, emitting gravitational waves. Now, one of the black holes is 3.5 times more massive than the other, and so the simulated gravitational wave signal is consistent with the observation of GW190412 made by the LIGO and the Virgo gravitational wave detectors. The gravitational radiation is translated to colors around the black holes. The color transition from blue, representing weak radiation, to red, representing strong radiation. The strain is also shown at the bottom of the screen here. Right. Just allow the video to finish off. Right, so you can now see that it's spiraling. It's about to merge. Video is slowed down for that. Anyway, so it merges. That's, okay, let's move on. Okay. Now, not much later, we had GW190521, which at this point is the most massive binary black hole detected with component masses of about 85 and 66 solar masses. So really heavy black holes collided to form a remnant black hole of about 142 solar masses. This is very exciting because the remnant mass is called an intermediate mass black hole. Intermediate mass black holes have been postulated for quite some time, but there was no convincing observational confirmation before this particular detection. Again, the video to the left is a numerical simulation of two black holes that are consistent with GW19 0521. The black holes are large and have nearly equal masses, with one only 3% more massive than the other. So you can again see the strain at the bottom of the screen. Okay. Then what happened? Then in August 2019, we observed GW190814, which is also a very exciting, because it is also a highly asymmetric binary with a mass ratio of 1:10. But the mass of the secondary component of the binary was rather puzzling, as it was higher than the heaviest known neutron stars, but lighter than the lightest known black hole. So it sits in this awkward place mass-wise, where it could be a black hole binary or a black hole neutron star binary. So it still remains a mystery, and gives a lot of speculation. Again, you see the simulation to your left, and this is consistent again with two black holes, where consistent with like GW 190814, where two black holes, where one is 9.2 times more massive than the other. Such high mass ratio amplifies the gravitational wave signals in the non-dominant or higher modes. So this is basically the dominant mode gravitational wave radiation that you see, which is generally what we see for most of the equal mass binaries. But here you can also see some of the other the non-dominant or higher modes gravitational wave that are being amplified. Right. Okay. So then, very interestingly, what happened in Jan 2020, the first we had the first confident detection, NSBH detection, or neutron star black hole binary detection. And this is just based on the masses. So we had two detections, GW200105 and GW200115. And so again, this is we're calling it an SBH, just based on the masses that we have observed, masses of the secondary component of the binary that we have observed. The other event which is given here, which is 190426, is basically a marginal NSPH candidate, and this is obviously GW1908 14. The interesting thing is none of these observations had any electromagnetic counterpart. And this is why this is so, is we try to understand the simulations. So the first simulation, the one at the top here, shows that the neutron star gets tidally disrupted as it merges with the black hole. So as the neutron star approaches closer to the black hole, the tidal forces overpower the star's self-gravity, leading to this disruption. Right now, here the black hole is twice as massive as the neutron star in the simulation. And once you see the tidal disruption, you can see that in the electromagnetic regime. But the simulation that you see now is consistent with GW200115, where the tidal disruption of the neutron star doesn't happen, as it is engulfed by the black hole before this disruption can actually happen. And so you see no electromagnetic observation. And this is one of the plausible reasons why we don't see electromagnetic observations for all these events, because they were actually engulfed before the disruption can happen. Okay. So we talked about some interesting individual events, but now we are going to look at these events on a population basis. All right. So we have reasonable statistics now. We have 90 detections, so we can look at underlying astrophysical distributions that we get from these observations. So in particular, if you look at the mass spectrum of the black holes, we find that the primary mass distribution is consistent with that of power law distribution with a Gaussian feature with a peak around 34 supermasses. And you can see the profile for both GWTC2 as well as for GWTC3. And you see that the spectrum turns over quite sharply at around 7.8 solar masses. Right. So now, for the black hole spins, the story is also quite interesting. Here we show two spin parameters, the chi effective, which tells us about the aligned spin components parallel or anti-parallel to the orbital angular momentum, and chi p are the ones orthogonal to the orbital angular momentum, which gives an indication of precession. So we see from our observations that the underlying population is consistent with an astrophysical population that peaks at a positive chi effective, and which is also consistent with most of the black hole spin observations which are small and positively aligned, but there is a tail in the negative direction. Also, there is a weak evidence of precision in the underlying population. Okay. Finally, I'm going to finish off by talking about tests of fundamental physics that we can do from these observations. I will just talk about one particular test, general relativity, that I'm personally involved in. The test is called the spiral merger ring down consistency test. So the mass and the spin of the final black hole is basically calculated from the inspiral part of the signal and from the merger ring down part of the signal. If GR is correct, these two estimates from the two different paths should be consistent. So we define mass and spin parameters which checks this consistency, which are given here, and 0, 0 is basically the GR value. Okay. So what we see is that the distribution that we get from this binary black hole observations is also consistent, which is given by this gray region here. It's also consistent with GR, so it includes the zero point with certain statistical uncertainties. We have found no conclusive evidence beyond Einstein's theory of gravitation from all these different tests till now. Okay, to summarize, it has been an exciting 4.5 years from 2015 to March 2020, where we have found a total of 90 confident detections. Majority of this events are binary black holes, but with a very diverse range of mass and spin. We have observed asymmetric binary first observation of intermediate mass black hole, confident NSPH detections. We have observed two BNSs, 170817, and again, there's another one, 190412. I hope this is just the beginning of the excitement gravitational wave era, and we will soon resume observations at the end of this year with Pagra detector in Japan joining in, and hopefully soon LIGO-India will join operations. You can see the artist impression of the LIGO-India detector and also information about social media handles if you want to keep yourself updated. And thanks a lot for your attention. And I hope this picture is much more clearer to you guys. Hello, everyone. Thanks again for your attention. If you have any further questions, can you please type again in the chat box, please? I don't see any questions. Okay, so I just want to say a couple of things, and if you have any questions in between, please do type in your questions. So I heard there were a couple of questions before about gravitational wave data science, and I okay, there is a question. So do you release the data for mathematical evaluation on neural network on BOINC platform? So I'm not aware of what BOINC platform is, but but the data is publicly available. So if you can, I'm guessing you can use it in whichever way you want to, if that helps. So I'm really not sure what this BOINC platform is. Sorry. Is it possible that you can type in a bit more information about what this platform is about and what it does? The charge of black holes and neutron stars. Okay, that's a good question. So we can, in a way. So for the say, if we think that a black hole is charged, and if we look at the ring down signal of the black hole waveform, and the ring down signal is given by what we call the quasi-normal modes. And if GR is the theory, we know exactly what should be the quasi-normal modes given the three hairs, which is the mass, the charge, and the spin of the black hole. And so we can find out the estimates of both the mass of the black hole, the charge of the black hole, as well as the spin of the black hole. We generally assume that black holes are like, it can't hold the charge for really long. So we expect that we will get the estimation of the charge to be consistent with zero, as what we get from some of our a recent paper which has come out from some members of the collaboration. But it is true that we can estimate the charge of the black hole. Yeah. Okay, there's a project in Einstein Home on this platform. Yes. Okay. Yeah, I know you can use Einstein Home, but I'm really not. Okay. The next question: I cannot find any recent jobs for data scientists role in LIGO-India website. So I'm sure if you follow the social media handles which are given in my in my presentation, as well as if you go to the LIGO-India website, I'm sure you can approach various members of the LIGO-India, and they can direct you to the relevant job opportunities. This is for sort of, that's a good question. I'll give a couple of seconds more. And also in the meantime, I'm going to say that there are actually opportunities because of LIGO-India. There are now a lot of opportunities for projects for students, as well as upcoming professionals. And you can try to get in touch with different members of our group to find out what are the various opportunities available at various stages. Okay. since I don't see any more questions, I'm going to finally say thanks, and I hope you find you are interested about LIGO and LIGO-India. Thank you.
Thank you very much, Shashwat and Apratim, for this very interesting session. If you have any more questions for them, you can type them out in the chat box. So next up, we have the much awaited launch of the astrophotography virtual gallery, AstroPix. So if you've been following us on social media, LIGO-India organized an astrophotography webinar series from mid-November until mid-December last year. At the end of the webinar series, we announced a contest, and the entries were simply spectacular. This webinar series featured some of the most well-known astrophotographers from the country. So, on the occasion of the National Science Day, we are very excited to launch the astrophotography virtual gallery, AstroPix. Take a look. I hope you enjoyed watching the presentation of the gallery. You can view these astrophotographs along with their specifications on the LIGO-India website at www.ligo-india.in/astropix_gallery. On the occasion of the National Science Day, we are very pleased to also announce the launch of the LIGO-India Astrophoto Calendar for 2022. You can also grab a copy, so keep your eye on our social media pages. We will be sending out the details very soon. So next up, we have the National Science Day theme for this year, which is Integrated Approach in Science and Technology for a Sustainable Future. So to highlight this year's theme, we have the next session just for you. So as you know that LIGO-India has also this theme as a very central role in its local, national and international level. While the project is coming up in the Hingoli district of Maharashtra, it also requires expertise from leading national institutions as well as being part of an international global array of gravitational wave detectors. And this project also requires expertise in diverse fields such as laser, vacuum, optics, data science and much more, leading to a development of cutting-edge technology in India and a synergy between research, industry and engineering. So let's look at some of these areas in the upcoming session called GW Science Meets Technology. Here we will have virtual visits to some laboratories and gravitational wave science exhibits. First we have a visit to the PQM lab, the Precision and Quantum Measurement Lab at IUCAA, led by Professor Shubhadeep Dey, followed by several gravitational wave exhibits. The Vortex as an Analog Black Hole by Suresh Doravari from IUCAA, the Eddy Current Damping in LIGO Suspensions by project student Richal Abang, LIGO-India Suspension Training Module by Suresh and his project students. Then we will go over to the mock LIGO control room with Shivaraj Kandaswamy along with his project students. We also have a couple of GW Science exhibits presented by Ashish Maske, an IUCAA student. The first is Michelson interferometers to detect gravitational waves, and we also have seismic isolation using pendulums. Over to you for the lab visit and GW Science exhibits.
Here are a few visuals of our lab. The work area, where lab members are working on the design and simulation of various components. This is the lab area, where lab members are building and testing various parts of the optical frequency reference.
Welcome to IUCAA's National Science Day 2022. I am Dr. Suresh Doravari. I work in the LIGO-India group at IUCAA as a research faculty. Today I would be introducing you to some demonstrations we have at IUCAA. Today I would like to demonstrate a water vortex for you. Our interest in water vortexes is because they are analogous to black holes, and some of the black hole physics can be demonstrated and studied in a well set up water vortex. Such as we can, for example, demonstrate the existence of an event horizon. We can demonstrate something called super radiance, where a passing gravitational wave, for example, can pick up energy from a rotating black hole. Such experiments have been demonstrated in universities abroad. You will find links to that at the end of the talk. In today's demonstration, we have set up a water vortex in which we have continuous circulation of water from a lower reservoir to an upper reservoir. In the lower reservoir, we have a water pump which we got from an aquarium, and the water is pumped into the upper reservoir through a faucet on the side, which sets up a circulation of water. And in the upper reservoir, we have a hole at the bottom through which the water returns to the lower reservoir. In this flow of water due to this continuous circulation, we have a vortex which forms in the upper reservoir that you can see very clearly due to the light from the back. We have also, in order to visualize this, the entire the funnel that you see there, we have set up a laser. Usually the laser would just cast a single spot of light, and in order to spread the light into a vertical sheet, we have used a glass rod acting as a cylindrical lens. You can see the light which is spread out into a single line, which is falling on the funnel there. One of the phenomena we can demonstrate is the way waves on the surface water waves are deflected by the flow of water, and there would be a point inside the vortex where the water waves are unable to escape and come out. That would in effect be an event horizon. This is similar to what is generated when a boat moves fast through water. We have a bow wave which you can see forming here as a kind of a cone that expands from the tip of the screwdriver there. As we move that point closer and closer deeper into the funnel, we see that the direction of that cone continues to turn towards the interior of the funnel, and as the cone turns, the exterior of the cone would at some point become horizontal, and beneath that point the waves would not be able to escape from the funnel upwards, and that would be an analog to the event horizon of a black hole. Let's watch it again. We first see a formation of a bow wave, and as we approach the center of the black hole, we see a funnel forming and a bow wave which is like a V-shaped object which takes off from the tip of the screwdriver. And as we go deeper into the black hole, as we go deeper into the center of the vortex, this funnel turns, and we will reach a point where the waves generated will not be able to escape from the vortex. If you are excited by this particular demonstration, we have included some references at the end of this talk where you can pursue this kind of an experiment in research laboratories, as well as at home, where you can set up your own demonstration and study vortices and their physics. Thank you, and wish you a very happy National Science Day.
Hello everyone, my name is Richa Labhang. I am a project student at LIGO-India team in Ayuka. I am working with LIGO-India project, and I am working with Dr. Suresh Doravari. So today we will be talking about the projects that we are doing as project students over here in LIGO lab. So advanced LIGO are the detectors that uses laser interferometers to detect gravitational waves, and the mirrors that are suspended inside these detectors, they are suspended using 4-stage pendula which isolate the ground vibrations. So here at LIGO-India lab, we have used single stage suspension to demonstrate what goes exactly inside the LIGO-India tubes, and our attempt is to improve this technology. So this suspension sometimes uses eddy current damping to isolate the ground vibrations from the mirrors. So we will be seeing this phenomena today using a demonstration. So, before moving to the single stage suspension which we have designed in our LIGO-India lab, we would like to have a look at the eddy current damping which we have used for the single stage suspension passive damping. So, here we have a simple setup. We have a string of magnets which is attached to a string. The string is attached to the frame of this structure and the magnets are suspended. Now, we are going to look at the number of oscillations and the time it takes to come to the string of magnets to come to the rest after it has been released from a certain height. So, first I am going to put this foam sheet beneath the string of magnets, and then I am going to gently pull up the string of magnets and then release it. So, just notice the time it takes to come to rest. So, as you can see, it approximately did 9 to 10 oscillations before it comes to rest. Now, I am going to replace this foam sheet with a copper plate. And now I am going to repeat the same motion of the string of magnets. I am going to take it up to a certain height and then release it gently. So, again you have to notice the time it takes to come to rest. So, you can see it hardly did 1.5 oscillation before it came to rest. So, this is the phenomenon of eddy current damping. So, what actually is happening over here is when a conductor moves in a changing magnetic field or vice versa, the eddy current loops are formed inside the conductor, and then this sets up a resistive force to dissipate the energy. And this resists the motion of the conductor. So, in our case the conductor, which is the copper plate, is actually stationary and the string of magnets were moving. So, the changing magnetic field due to the change in height induced the eddy currents in this copper plate, and then the eddy currents were generated in the copper plate, and then it resisted the motion of the magnets, and eventually the magnets came to rest. So, this is the same phenomenon which we have used for a single stage suspension passive damping, which will be demonstrated by Dr. Suresh Doravari. Thank you.
Thanks, Richal. We would like to show you how eddy current damping is used in a typical LIGO suspension. What we have here is a single stage suspension in which there are two wires which suspend a mirror holder. In the place of the actual mirror, we have put in a dummy aluminum mass for today's demonstration. Usually this aluminum mass in the center on which we have stuck a mirror would be a full 3-inch diameter mirror. At the back of the aluminum holder, we have stuck some magnets, and on this frame we have put some copper conductors which will then interact with these magnets and damp out the motion of the suspended mirror. We would like to show you how effective this is in by moving the copper tubes closer to the magnets and observing how the damping time significantly becomes shorter. For a start, let me set the mirror in oscillation, and then I will move the copper tubes closer for you to see how much the damping force increases. I am now going to bring a magnet close to the mirror, which effectively deflects the mirror in a direction. I am going to release the mirror from a large deflection, and then Richal here would be timing the amount of time it takes for the amplitude of the oscillation to decrease by a factor of E. So, presently the amplitude I am going to release from is more than this value A, which is roughly 20 centimeters of deflection of the spot that you see there. So already the presence of aluminum around the magnet has, I think, provided significant amount of damping. So there is certain amount of damping already present. Now I am going to move the copper tubes closer, and that should further increase the amount of damping. I am going to use a glass rod to move the magnets closer to, move the copper rods closer to the magnet. There is roughly 2 millimeters or so of space between the magnet and the copper pieces. I am going to deflect. Okay, I am about to release. Rachel, you are ready to time it?
Yes.
It's hardly a couple of seconds and it already comes to rest. Yeah, so this particular eddy current damping is one of the ways in which we reduce the motion of the mirrors, especially in smaller single stage suspensions in advanced LIGO. Such projects which we use for both demonstration and training purposes are actually devised as training modules as part of our LIGO-India training program, and they are available for colleges and institutions across India where the students are interested in learning such technology associated with gravitational wave detectors. And we would be happy to work with you in setting up such experiments and learning this technology. We will also provide some references in an associated slide. You can follow the work that we do on our websites, as well as the work that goes on globally in gravitational wave detectors. Thank you, and wish you a wonderful National Science Day. Hello, welcome to the National Science Day 2022 of IUCA. I am Dr. Suresh Doravari. I work in the LIGO-India group at IUCA. As you all know, LIGO-India is a mega science project, and IUCA is one of the 4 nodal institutions which together are tasked with building LIGO-India and operating it. In preparation for LIGO-India, we have set up an extensive training program which is designed for college students and for our own in-house personnel to train ourselves in installation and commissioning tasks which are challenging in LIGO-India. One of the modules that we are presenting today pertains to the LIGO-India suspensions, and all the various technological skills that are necessary can be built, can be developed within these training modules. I have several students working with us. Varun and Ahan today will be talking about these training modules. They will talk about all the details of the entire training module that is in front of you.
Hello, my name is Varun Deshmukh. I am a project student working with Dr. Suresh Doravari. Today I will be demonstrating the suspension training module that we have designed and built. So this module is based on the hammock suspension that is currently used in LIGO, in the advanced LIGO. So the suspension is used to suspend a 3-inch optic. The optic is suspended from using these 200 micron diameter wires which are attached to these blade springs, which provide a soft suspension point. So the motion of the optic is monitored or sensed and controlled using these modules here called OSEMs, which I can show here. So these OSEMs essentially have a voice coil actuator and a shadow sensor which measures the displacement of the optic. The signals produced by the shadow sensor are go through this module that we have designed and built. So these electronics essentially have a coil driver and a transimpedance amplifier, wherein the coil driver actuates the voice coil actuator and the transimpedance amplifier amplifies the signal from the shadow sensor. Yeah, so after we have conditioned the signals, they go through this data acquisition system here to the computer, which analyzes the data and sends a feedback through the same route and hence drives the voice coil actuator, which is used to dampen the motion of the optic. So you can see that when I gently tap on the optic here, the signal from the sensor, the shadow sensor that we have, can be displayed on the monitor here. And apart from this, we are also developing the feedback control system, which is used to dampen the motion of this optic.
Hello, I'm Ahan Parsale. I'm a third year BSc student at the Interdisciplinary School of Science in Pune University. I'm working on my third year project over here, which is a great opportunity for me. My project involves an optical lever, which is a setup as you can see over here. We have a laser source over here and the beam of light passes straight through onto a mirror. This is a mock-up mirror, of course, from where it will go forward onto a sensor, a detector over here. When the spot moves over here, we can say what the motion of the mirror is over there. It acts as an out of loop sensor for the motion of the mirror. This is a very important part of LIGO interferometer sensing and control, and my project specifically involves estimating the noise sources and the noise budget involved in the optical lever.
Thank you, Varun, Ahan and Richel. As you can see, we have several college students who work with us on our training programs, and these training programs are specifically designed for adopting as part of either the college curriculum or as extracurricular club activities like the astronomy club or the science club in your colleges. We would be happy to help you set up these activities and share the designs and offer advice in pursuing these studies in your own facilities. You will find some references in the link right next to the link to this video, and we welcome you to take part in this adventure with us. Thank you.
Hi everyone, my name is Shivraj. I am a scientific officer here at IUCA. Today in this video we are going to have a quick look at the mock control room that we have set up at IUCA. This is control room is for LIGO system. So LIGO is a large scale experiment to observe gravitational waves that has been set up at the US by the LIGO collaboration. So here is a picture of the aerial view of the LIGO observatory. As you can see, this is a large scale facility. It's actually a 4 km long enhanced Michelson interferometer to detect gravitational wave signal. As any other large scale facility, it's always good to have a common like a control room infrastructure where you can monitor what's happening across the observatory. This is also established in other large scale experiments like ISRO, NASA and CERN. So LIGO also has set up such infrastructure. So this is a schematic of the LIGO interferometers. Not only you want to monitor what's happening at the observatory, but we also need to control what is happening at the observatories, like at the various parts of the instrument. For example, here is a schematic of the LIGO interferometer showing various mirrors in the interferometer. To operate the interferometer with high sensitivity, we need to keep the location of these mirrors well positioned. To do that, we need to first measure the position of these mirrors, then apply some kind of control signal, what we call feedback control, to keep the position of these mirrors fixed. And for that, we need a common place where we can do this process. And for that, also this control room actually very useful. So not only we look at the position of the mirrors and the lasers, but we also look at what else is happening around the observatories. For example, we have placed many other sensors around the observatories that monitor, for example, seismic signal, sound vibrations, or light levels, or electromagnetic interference, and seismic vibrations, temperature sensors, wind sensors. So we have placed many different sensors. We also have to monitor these sensors. So this control room acts as like a gateway to monitor these sensors also. So this is an picture of the control room at LIGO Livingston Observatory in US, and you can see there are many screens at the top that showing different figures. You can also see like white colors. They are basically looking at the lasers at different parts of the instrument. And you can also see other screens that shows like lines. These are basically signals coming out of the interferometer at different parts. And you can see at the bottom there people are sitting in front of the computers, and from these computers you can talk to any parts of the instrument. If you want to change something, you can change from these machines, and that is what these people are doing. So this is the main control room that is used for most of the activities at the observatories. This is for LIGO Livingston, and there is a similar control room exists in the LIGO Hanford Observatory. So here we are trying to replicate a small model of this control room, so that we can also see what is happening at the observatories and also get trained ourselves. So when LIGO India comes up, we will also have a control room like this. So it will good to have a small scale here, so that people get trained on it. Okay. So here there is another screen that actually shows a seismic signal at what is happening at the seismic motion at the observatory. It is actually at current time. So the far left is the current time, and the far right far right is the current time, far left is the 6 hours before, and so this is basically showing this last 6 hour span what is happening to the ground vibrations at different parts of the instrument. This is the same screen you would also see on the far left on the actual LIGO control room. So this basically tells us what is happening to the ground motion across the observatory, and you can see that this is more or less constant. That means there is no significant activities happening in the last 6 hours. For example, if there was an earthquake of like maybe Richter scale of 6 in somewhere in the globe, you would see a huge spike here. Since for the last 6 hours, I think most of the world is mostly quiet, so you don't see any high spike. So if you see a spike, that means there is an earthquake. During that time, it's very hard to operate our instrument. So what you can do is that either you can change the configuration of the instrument so that you can operate, or you can do some maintenance work in the meantime, so that you will use that time for something meaningful. So this is one of the screen, and if you look at the LIGO control room screen, there are many other screens. So here we have only like 2 TVs, so that's why we have displaying only 2 of these. But in actual control room we have many different displays, so that will be displaying many other informations. This is overview of what's happening at the observatories. But if you want to actually interact with the instrument, you need to use these computers. So we have set up 2 computers that are similar to what the people are working there. And here in this computer we are basically looking at what is happening at the LIGO Livingston Observatory, and on the right side this is showing what is happening at the LIGO Hanford Observatory. Shankar here, he is also our LIGO India staff, and he will show that he will explain the PSL, that picture that we have displayed in this screen.
Hello, my name is Shankar. So I am working as a scientific officer at IUCA. So I will be explaining about the site map. So here you can see in the screens, like this is the site map for MEDM skins, which is at LIGO Livingston. So these are the various MEDM skin associated with the various subsystems. So in this skin you can see that this MEDM skin for laser stabilization. So this graph here you can see, like this graph shows that stabilized output power of the laser. So you can see this is very stable.
Okay, so this is a screen from the LIGO Hanford Observatory. So on the previous screen you were looking at the things happening at the LIGO Livingston. Here we are looking at what's happening at the LIGO Hanford Observatory. Specifically, we are looking at one of the main mirror in the LIGO Hanford Observatory. So this is the schematic of that main mirror. We call quad suspension, means the mirror at the bottom is suspended through 4 stages. So, this is a quad suspension. So, here is the control of that quad suspension using the what we call the medium screens. These are the infrastructure that is used in many other large scale facilities is CERN to control various things that are happening. So, we are using the same infrastructure called EPICs to control what's happen, how to control these mirrors. So, here you can see that there are 4 stages on the left side, you can see, which resembles the 4 stage quad that we have in this picture. So, we want to basically we want to control the motion of the mirror at the bottom. That can be controlled by directly controlling the motion of the mirror at the bottom, but also by controlling the motion of the other mirrors at the top stages. So, we call this hierarchical control, so that it will be, we will basically distribute the controlling load for different stages. So, it will be much easier instead of just putting all the load to that bottom stage. And if you look closely, you can see that there are numbers that are changing, which means that there are signals coming in, and those signals that we take the signal, we some kind of data processing, then create some kind of control signal, then we send the signal to control these mirrors. So, there are actuators. If you look closely, there are behind these mirrors, there are like magnets. So, we basically send a electromagnetic signal to control those magnets, and because in that way we are basically controlling the position of the mirrors, and that is what happening in these screens. And if you look closely, these numbers are not changing very much, they are almost like stable, which means that the position of the mirrors is kept stable. And these numbers are for example, the pitch, the number is in the units of a microradian, in this like 1/1,000,000th of a radian, and you can see that the number is not changing significantly in the sense the position, the angle of this mirror is not changing more than 1/1,000,000th of a radian, which is very small. In our day to day life we do not experience these small changes, but this is very important for these high sensitive instruments, and that is what happening here. So, this is the quad stage. So, we will have similar screens for different other mirrors in the interferometer. There are like 3 stage mirrors, single stage mirrors. So, we have different medium screens to control those mirrors.
We have installed the CDS system for the control room, so that the data for the observatory, so we can get the data and display the various monitors, and for user modules for CDS systems. Some users can analyze the data for the CDS system.
Hi everyone. So, we looked at the various systems that we have installed here as part of the mock control room. This was with the help of our scientific officer here at IUCAA, Harshan Savan. We were able to install these systems and up and running. Now, people are able to use these systems and to understand what is happening at the observatories. They are able to look at these screens and understand how the data is flowing and what is happening at the observatories. So, they are able to do those trial and error by themselves. So, I hope this will grow in larger scale as we see in the actual observatories. We hope we will actually, when the LIGO-India comes up, we will also have a similar control room where we can do large scale analysis, and also we hope that people can also visit these observatories and get to know in person what is happening at the observatories. Okay, thanks everyone. Thanks for watching the video, and happy National Science Day, and hope you also enjoy the other videos that we have been making.
Hello friends, I am Ashish Maske. I am a scientific and technical officer here at IUCAA. In this demonstration, we are going to see how a Michelson interferometer is used to detect gravitational waves. So first let us see a simple setup of a Michelson interferometer. So in a Michelson interferometer, we have a source of light which is a laser. There is a lens which expands the beam, then there is a beam splitter, and there are 2 mirrors kept perpendicular to each other. So the light will start from the laser, the lens will expand the beam of light, the light will fall on the beam splitter. The beam splitter actually splits the light into 2 parts. One path will continue straight to the front mirror, and the other path goes to the perpendicular mirror. The mirrors will reflect this light, and then what we see on the screen here is basically the superposition of these 2 beams. So on the screen you can see a fringe pattern.
So this is basically occurring due to the superposition of two beams. So we have created some smoke so that the beam of the laser is clearly visible. The beam falls on the lens and you can see that it expands. It reaches the beam splitter and is split into two parts. One goes to one mirror, other goes to the other mirror. It is reflected back from the mirrors and is combined and comes out of the beam splitter. So now we will see how a Michelson interferometer can detect gravitational waves. So here is a animation showing the working of the Michelson interferometer. So you can see we have a similar setup with a laser, a beam splitter, two mirrors perpendicular to each other and a screen. So light starts from the laser, it reaches the beam splitter and it is split into two parts. So it reaches the end mirror and it is reflected back to the beam splitter. When both these beams combine, they form a fringe pattern on the screen. So now imagine, due to some reason, the relative position of this mirror is changing. In that case, the two beams coming out of the interferometer will either constructively or destructively interfere, and that will give us a bright or dark spot. And this is actually our gravitational wave signal. So if the gravitational wave is incident on the interferometer from the top, then the mirrors will start moving and they will form a dark and bright spot at the output of the interferometer. So this was the animation showing how a Michelson interferometer will react to a gravitational wave. A gravitational wave is actually a distortion in space and time. So if a gravitational wave passes through 2 points in space, then the distance between these 2 points will stretch and contract. So it can be seen here in this animation where we have placed objects in a ring and a gravitational wave is incident on this ring. So the ring will stretch and contract in a very particular manner. Now why a Michelson interferometer is a natural choice is because of this effect. So as we see, when the horizontal objects stretch, the vertical diameter of the ring is compressed, and vice versa, when the vertical arrangement is stretched, the horizontal arrangement is squeezed. Now the Michelson interferometer can sit perfectly in this arrangement. So the beam splitter can be at the center and the two perpendicular mirrors can be at the two ends of this ring, and hence a Michelson interferometer is a natural detector for gravitational waves. So we have another Michelson interferometer set up here with some modifications. So similarly we have a source of light which is a laser. There is a beam splitter in the middle. The beam splitter splits the light. It goes to the two mirrors and it comes back and falls on the detector. The modification here is that one of the mirrors is mounted on a piezoelectric crystal. Whenever we apply any voltage to the piezoelectric crystal, it will start oscillating. The light coming out of the interferometer falls on a photodetector. Now what we have done is we are providing an oscillating signal to the piezoelectric crystal. What that will do is it will change the position of that mirror in a oscillating manner. At the output of the interferometer, there is a photodetector which converts the light falling on the photodetector into electrical signal, and we see that electrical signal represented here in this plot. So you can see that the voltage is actually oscillating. This is because the piezoelectric crystal is also oscillating. Now let us log the interferometer. As you can see, what has happened is the crystal has stopped moving at a very particular position. The output intensity is now maintained at half of the maximum intensity. This configuration is called a logged interferometer. That means the relative position of the optical components in the interferometer will stay fixed. So in our setup, all the optical components are mounted on a platform, In LIGO, all these optical components are suspended with pendulums. The reason for doing that is as follows. So, if I try to create some disturbances in the ground, let us say if I try to bang on the table, then you will see those disturbances appearing at the output of the interferometer. You can see the disturbances appearing here. To avoid these ground disturbances from reaching our optical components, we suspend them such that the pendulum will actually attenuate most of these ground vibrations. So, in this demonstration, we saw how a Michelson interferometer operates and how it can be used to detect gravitational waves. India is also planning to build a gravitational wave detector, and as you see, we require students and experts from all fields of engineering and science. So, we invite you all to join us in this endeavor. If you like the video, please share and subscribe. If you have any questions, please write them in the comment section, and I wish you all a very happy Science Day. Hello friends, I am Ashish Maske. I am a scientific and technical officer here at IUCA. In this demonstration, we are going to see how pendulums help us in detection of gravitational waves. Laser Interferometer Gravitational Wave Observatory, or LIGO for short, is a gravitational wave observatory where we try to detect gravitational waves. So, gravitational waves are actually distortion in space-time. So, if we have 2 points in space and a gravitational wave passes through these 2 points, then the distance between these 2 points will stretch and contract. So, to detect this change in length or change in distance between 2 points, LIGO uses 2 mirrors, and they measure the distance between these 2 mirrors very precisely. So, there are several challenges when we want to detect gravitational waves. So, in LIGO, the distance between these 2 mirrors is about 4 kilometers. To detect gravitational waves, we need a very high sensitivity, or we need to measure the displacement between these 2 mirrors very precisely. So, how much sensitivity do we need? So, for detecting gravitational waves successfully, we need to measure displacements of the order of 10 to the power minus 18 meters. 10 to the power minus 18 meters is a very small number. It is in fact 1000 times smaller than the size of a proton. So, you can imagine how many challenges one can face while measuring the length between these 2 mirrors to that precision. One major challenge is the ground vibration. So, there are several human activities like there is traffic, there are people walking around, there is heavy machinery operating, and as well as there are several natural phenomena which give rise to ground vibrations. So, if we use a very sensitive measuring device and place it on the ground, we will see that this ground motion is roughly about of the order of 1 micrometer, that is 10 to the power minus 6 meters. And we remember we have to measure 10 to the power minus 18 meters. But if the ground itself is moving at a few micrometers, then detecting effects that are occurring at 10 to the power minus 18 meters will be impossible. So, how does LIGO achieve this sensitivity? So, what we can do is we can use pendulums. Here you can see a simple pendulum. A simple pendulum is basically a mass tied to end of the thread. So, this is a heavy mass, and you can see if I move my hand very slowly, the pendulum actually follows my hand. The mass at the end follows my hand. If I slowly increase the frequency of oscillation of my hand, the pendulum will start swinging more and more. At a particular point, the pendulum will swing at its maximum amplitude. So, you can see I am barely moving my hand, but the pendulum is oscillating to a very large amplitude. So, this is called the resonance frequency of the pendulum. Now, what happens if I move my hand above resonance frequency? You can see above resonance frequency, the pendulum barely moves. My hand is moving at a very high frequency, but the pendulum is staying stationary at one position. So, we can make use of this effect to isolate our mirrors from ground vibration. So, here we have a setup of a pendulum. This is a two-stage pendulum. So, why do we need two stages? Suppose we want to detect gravitational waves at 100 Hertz. So, what we can do is we can make the resonance frequency of the pendulum very low, let us say 1 Hertz. If you remember in our previous demonstration, we saw that the pendulum does not oscillate for frequencies above the resonance frequency. So, any vibration above resonance frequency is basically attenuated by the pendulum. Now, we get some amount of attenuation, but if we want even more attenuation, what we can do is we can add multiple masses on this pendulum. So, it becomes a multi-stage pendulum. For a two-stage pendulum, we get more attenuation at higher frequencies than just a single stage pendulum. In LIGO, we actually use 4-stage pendulums. To demonstrate this effect of attenuation by pendulum, we have created a simple setup. So, we have a source of light, which is a laser. The laser falls on a mirror and then it is directed towards a pendulum. We have a blade attached at the bottom of this pendulum and the light partially falls on this blade. The light then goes to a photodetector. The job of a photodetector is basically to convert visible light into electrical signals, and we can see those electrical signals on the oscilloscope. So, if the pendulum moves due to some reason, then it will cut out this light falling on the detector, and that is how we can measure the motion of the pendulum. Here we have an actuation coil at the top and the pendulum is suspended from this actuation coil with the help of a rod. So, if we provide any actuation to this rod, the pendulum will actually start moving accordingly. So, for very low frequencies, if you remember, the pendulum should follow our actuation. At resonance frequency, you will see a very large amplitude, and any frequency above this resonance frequency, you will see very little motion. Basically, the disturbance from the actuation coil will not reach the pendulum for higher frequencies or frequencies above the resonance frequency. The resonance frequency of this pendulum is close to 1 Hertz. So, what happens if we give the actuation frequency lower than 1 Hertz? So, let us say I give 0.1 or 100 millihertz frequency to the actuation rod here. You can see that for frequencies very low or lower than resonance frequency, the pendulum actually follows the actuation. On the oscilloscope, the pink curve is the actuation frequency or the actuation signal, and the yellow curve is the motion of the pendulum. So, you can see that the pink curve and the yellow curve follow each other. Now, what happens if we go very close to the resonance frequency? So, as you can see, close to the resonance frequency, the pendulum actually starts oscillating with a very large amplitude. You can see this effect on the oscilloscope as well. The pink curve is our actuation frequency or actuation signal, which is close to 1 Hertz, and the yellow signal is our motion of the pendulum. You can see the amplitude has also increased for this signal. So, this is the effect of resonance frequency. Now, we increase the frequency of actuation even more or above resonance frequency and see what happens to the pendulum. Now we have provided the actuation frequency 10 Hz, which is much higher than the resonance frequency. You can see the actuating rod is actually moving at 10 Hz, but the pendulum is staying stationary. So pendulum is basically attenuating the high frequency oscillations. You can see the effect on the oscilloscope. The pink curve is again our 10 Hz actuation signal, and the yellow curve is the motion of the pendulum. You see the wavy nature in the yellow curve, and that is basically the resonance frequency of the pendulum, but you do not see any higher frequencies, or you do not see the 10 Hz oscillations in that yellow curve. So the pendulum has basically attenuated the 10 Hz signal. So in this demonstration we saw that the pendulum is very good attenuator for any ground motion for frequencies above its resonance frequency. So LIGO uses this technique to isolate the test masses from the ground vibration. Seismic isolation is one of the major subsystems of LIGO detector, and you can see how LIGO achieves the required sensitivity using these techniques. If you have any more questions regarding this demonstration, or if you like the demonstration, please like and share the video. You can ask your questions in the comment section, and I wish you all a very happy Science Day. You can ask your questions in the comment section, and I wish you all a very happy Science Day.
We hope you enjoyed the virtual lab visits and the gravitational wave science exhibit demonstrations. One partnership program between India and UK has been particularly successful in bringing science and technology skills and skill training required for the LIGO-India project and to encourage entrepreneurial activity. We have with us Professor Giles Hammond from Glasgow University, who will be reviewing the success of the Newton-Bhabha collaboration. Let's have a look.
Hello there. My name's Professor Giles Hammond from the Institute for Gravitational Research at the University of Glasgow. It's a pleasure to be talking to you on your National Science Day. I'm going to speak about gravitational wave astronomy and talk about some of the fundamental science opportunities and also some of the applied spin-offs. So I work in two areas at the University of Glasgow. So the one on the left-hand side there you see is our work on the advanced LIGO detectors, and this is to develop hardware, suspension hardware for these long baseline interferometers that are currently operating in the United States. Of course, in India, you're going to also be getting a LIGO-India detector, which looks very similar to the LIGO US detectors. But I also have a second research group, and that really works on the development of precision gravity sensors. And that's a direct spin-off from some of the work that we've been doing on the gravitational wave suspensions. So in this talk, I'm going to focus a little bit on the left-hand side, which is all about the fundamental science, really looking at the universe in a new way using gravity rather than electromagnetic radiation. But then also, I'll then switch gears and talk about some of the opportunities that exist for getting that technology out into more applied and spin-off opportunities, possibly even leading to starting of new companies. So we'll start with the fundamental science. So you've probably seen some lectures already today about gravity and Einstein, but I do have one slide that just talks a little bit about gravitational waves. So of course, our theory of gravity is described by general relativity. So that's currently our best theory of gravity. And that's a purely classical theory. So it states that when you put matter and energy into space-time, then that curves space-time. So you can see there on the left-hand side a picture. Imagine this was a rubber sheet, and the yellow object was a ball. And if it's a heavy ball and you drop it into the middle of the sheet, then what you find is there's local curvature. And it's curvature of that sheet that when you roll the small ball, the little green one that goes around, then if there's local curvature, then that ball starts to move in a curved path. And that's really what we think as gravity, as described by general relativity. The only difference here is that rather than the rubber sheet, then we have space-time, and mass and energy curve that local space-time, and it's the motion of objects in that curved space-time that looks like the gravitational interaction. So John Wheeler, he had this very nice statement shown in the purple box, where he says that matter tells space-time how to curve. So what you put into space-time defines its curvature. And it's then space-time that then tells the matter how to move. So there's this very non-linear relationship between what you put into space-time and the effect of objects in the curvature. Now imagine that those two objects were large or heavy, and they were sort of orbiting one another rather fast, maybe hundreds of times per second, maybe the mass of a few times our sun. That's quite an extreme cosmological or astrophysical environment. What you get then is you get perturbations or ripples in space-time as these objects sort of orbit one another. And it's those ripples in space-time that we think of as gravitational waves. Those gravitational waves travel at the speed of light according to general relativity. And indeed, a few years ago, we measured a neutron star in spiral, and that did indeed show that the speed of light and the speed of gravity are the same to exquisitely high level. So we find that gravitational waves are caused by acceleration of massive objects, and we'll see in a few slides' time that you need massive objects in order to generate signals that you have any hope of detecting on the Earth. Now, what we do in gravitational waves, you can see those two little animations at the bottom. So that's a ring of test particles, and that's assuming the gravitational wave is going into the screen or out of the screen. And those test particles are sort of stretching and shrinking, and this is what we call quadrupolar motion. So part of the orbit, we find that there's a stretching, and then the other half of the cycle we find there's a shrinking. So that circle of diameter L increases or decreases its length by delta L. So we have this dimensionless number. This is called a strain when you take the ratio of two dimensions. That's a strain, just like heating up a metal bar. It can also have a strain. And we find that this parameter called H, and we'll talk about H a little bit later for typical astrophysical sources, is 2 from the fact that it stretches and shrinks, delta L over L. Now, in this case here, H is quite large because delta L is of the order, or 2 delta L is close to the value of L. So H is about 1 in these animation down here. We'll see that for our astrophysical sources, H is really much less than 1, and that's why it's quite a challenge to detect gravitational waves. Well, we've seen that we generate waves, gravitational waves, by accelerating masses. Of course, you know about electromagnetic waves. So there's a nice analogy between electrostatics and gravity. So on the left-hand side, we've got electrostatics, and we know that if we've got 2 charges, Q1 and Q2, then the electrostatic force between those is the multiplication of those 2 charges divided by a constant, 4 pi epsilon naught, and divided by the distance of those charges squared. Similarly, for gravity, if you've got 2 masses, m1 and m2, then the actual equation looks pretty similar. So the force of gravity is G, which is the strength of the gravitational interaction, m1, m2 divided by r squared. So these are both what we call inverse square laws. So there's a lot of symmetry between the electrostatic and the gravitational interaction. Now, if you want to generate electromagnetic waves, so here's a radio mast. So what you do is you take a charge and you accelerate it sort of up and down. And of course, if that charge is static, you get a static electrostatic field. But if that charge is accelerating, then you get a time varying electrostatic field, or what we think of as the electromagnetic field. And that's what we have as a radio wave being emitted by that transmitter. And similarly, if we take two massive objects and spin those around very fast, then we get these ripples in space-time, and that's what we see as a gravitational wave. And of course, these waves carry information, so we can tell about the sources, but they also carry energy away from the sources. So as the sources spin around one another, then their orbit decays, and eventually they coalesce. So we said that H was quite a small number. So this is what we typically see. So imagine we take two objects and attach them on the end of a bar. So maybe two one-ton sacks of sand, and you spin them around they've got a radius of about 2 meters, and you spin them at a kilohertz. That sounds like quite an energetic system. And then on the right-hand side, we've got two neutron stars, and their mass of 1.4 times the sun, spinning around each other at 200 hertz. But they're much, much further away. They're about 100 megaparsecs away, and that's close to the Virgo cluster. And then we can calculate this value of H. So this is how you calculate H. So this is a result from general relativity. And well, we're not going to talk about where this comes from, but we can actually make some sort of insight into what we think will make H bigger or smaller. So we've got this number here, G, so that's the Newtonian constant of gravity, and that's quite small. That's about 6.67 times 10 to minus 11. And then we've got c squared, and that's the speed of light. That's a big number. So G over c squared is small. So we know already that H is going to be quite small. Then we've got m over d. So as the mass goes up, then H gets bigger. And as the distance goes up, H gets smaller. So of course, for our neutron star, we win with having a large mass, but we lose because it's far away. And then you get this ratio here of v over c all squared. And that's the ratio of the sort of velocity in the orbit divided by the speed of light. So v over c should be close to 1. Otherwise, that is also a very small number. So when we calculate this for our two sacks at the end of a solid rod, then although we think that's a pretty extreme environment, it's nowhere near extreme enough to generate strong gravitational waves. So if we calculate H at 300 meters, we get a value of 10 to minus 37, very small. If we calculate it for our neutron stars, we get an H of 10 to minus 21. So it's 15 orders of magnitude larger. Although those stars, those neutron stars are much further away, because they're orbiting one another much closer to the speed of light, and they're much heavier, that means that the value of H is much, much larger. So we're never going to see a terrestrial source. We're never going to be able to make a terrestrial source of gravitational waves, but we can actually expect to see astrophysical sources. And then just to put that into context, remember again our stretching and shrinking objects. So if that L is 1 meter, then delta L is lots and lots of zeros and a 5 at the end. That's not measurable. Whereas actually, if we make those masses 4 kilometer separation, delta L actually is much, I say much bigger, but it's still a small number, but it's measurable. It starts to become sort of a few times 10 to minus 18 of a meter. So it's a fraction of course, about 1,000th of the diameter of a proton, but a measurable effect. And that's what we measure in our gravitational wave detectors. So we're doing this because it's a new probe of the universe. So we've always looked in electromagnetic wave bands, so infrared and gamma ray and cosmic ray. Gravitational waves gives us a totally new way of looking at the universe and a non-electromagnetic way. So back before we detected any sources, we weren't sure what we were going to find. But now we know that actually the cosmos is full of actually quite a lot of binary black holes, and also, of course, neutron star binaries. And sometimes you get a neutron star and a binary, a black hole together in a binary. So there's a wealth of information out there, and it's a completely new way of looking at the universe. A little bit like I sometimes say, the analogy is that it's like electromagnetic window in the universe is like seeing, whereas the gravitational wave window in the universe is like hearing. So it's a completely different way of looking at the world around us. So of course we have a number of detectors around the world, and we've talked about the LIGO ones already. So there's 2 LIGO detectors in the US, one in Hanford in the state of Washington, and one in Livingston, Louisiana. There's a German UK detector called GEO600. There's a French-Italian detector called Virgo. And then there's 2 detectors over here. So CAGRA is currently under construction, or actually starting to do science runs together with the LIGO detectors. And that's a cold detector in Japan. And then of course we've got LIGO-India here. And that's a detector that will look very similar to the LIGO detectors. So it's a 3rd LIGO detector in India. And there's a lot of work that you'll have heard about going on in order to deliver that technology. And we have a network of detectors because we need a network to locate the sources. Because if we're listening to a source, we have 2 ears, and we need those 2 ears to work out where the sources come from. So this is now showing why a LIGO detector is actually well suited to measuring gravitational waves. So what the LIGO detectors, you see this sort of arm in a sort of Y shape here. Or this right angle. Well, what we have is an interferometer, and that interferometer is looking along these 2 arms. And at the end we have mirrors, and then this is the test masses that are stretching and shrinking that we saw before. And what LIGO does is it sends a laser beam out between those 2 arms. As those arms move relative, then we start to see light in the dark port or output port of the interferometer. So what we're doing is we're looking at the phase of the light, and we're looking at the phase as the beam traverses down the arm lengths. So remember, those arm lengths are 4 kilometers in LIGO, and we measure a position sensitivity to about 10 to minus 18 of a meter. And that's what's needed to measure 10 to minus 21 of H. We can see there that we find that as the arms stretch and shrink, then we find that the phase of the light, or the brightness of the light, so we get constructive or destructive interference in the dark port of the interferometer. Now, of course, we don't let the light sort of go up and down in brightness. We actually have lots of what we call control systems to allow us to hold the operating point of the interferometer, always just a little bit off a dark fringe. Now, this task to detect gravitational waves started about 50, 60 years ago. You might say, why has it taken so long to detect gravitational waves? Well, I think the fact that it's such an immense experimental challenge, these values of H are so small, it's equivalent to detecting the distance to the nearest star to about the width of a human hair. So that gives you a feeling of the experimental challenge. And I think you'd argue that, measuring anything to the width of a human hair, even in the distance of, a lecture theatre or to the nearest sort of supermarket, is an extremely experimental challenge. Measuring to the nearest star to the width of a human hair is an unbelievable experimental challenge. And of course, it's taken a lot of technology to get us to that point. What does that technology look like? Well, that's the LIGO Livingston detector. In there is a high power laser. This is an entirely evacuated vacuum tube. And then we've got mirrors at the end, and we've got mirrors and optics in the inside here. Hanford looks very similar, except Louisiana there is quite wet. It's in the swamps of Louisiana, whereas Hanford is actually on a sort of arid plain, so it's more of a desert environment. But the detectors actually are sort of essentially copies of one another to make the sensitivity about the same. It's taken an awful lot of technology to detect gravitational waves, and I'm just going to sort of highlight just 2 or 3 of the key technologies. So this black curve is essentially what the detector sensitivity looks like. It's hard to see, but this is 10 hertz, this is 100 hertz, and this is a kilohertz. So we detect typically between 40 to a few kilohertz in the LIGO detectors. Now at low frequency, there's lots of noise sources. So you can see lots of noise kind of peaking at low frequency. And one of the big challenges is seismic noise. So the Earth is a very noisy place. So the way we get around seismic noise is we hang our mirrors off multiple pendulum stages. And then we have essentially isolation, not unlike the the suspension in a car. So at low frequency, if you go over a bump, then the whole car sort of moves up and down. If you hit, there's going to be a resonant frequency. So this is a mass spring system, so it has a frequency at which it likes to vibrate. If you hit the resonance, then it becomes very uncomfortable in the car. So what we do is we apply damping to reduce those resonances. And then at high frequency, the ground can move a lot. This is, imagine, shaking up and down going over bumps in the car. Whereas if you've got this mass spring, this is actually the main sort of cabin of the car. It's actually quite stable. So what we can do is we can actually cascade multiple pendulums from one another to get isolation. And we typically get our suspension systems provide about a factor of 1 million isolation from the ground. And then combining that with a seismic isolation system, we get about 1 billion or 10 billion reduction in the ground motion, and that allows us to get to 10 to minus 18 or 10 to minus 19 of a meter at 10 hertz. We also have what we call quantum noise. So the LIGO detectors are operating close to the fundamental quantum limits. And what that means is that when we look at, for example, a laser beam, so here's a laser, and what we find is that we can think of that laser as emitting photons. And those photons are like little packets of energy. So they can hit the mirror and bounce off, but they impart momentum to the mirror. And what we find is that because those photons aren't always quite the same number, so there's a statistical variation called Poisson noise, then what we find is we get a time varying force on the mirror, and that's called radiation pressure noise. So what we can do to improve that is we can reduce the laser power, because that reduces the momentum imparted to the mirror. But the problem with that is that we then have less photons. So we find that statistical variation in the photon number gets worse. And this is what we call shot noise. So to get shot noise better, we'd like to turn up the laser. So there's this sort of trade-off between having good performance in terms of shot noise and good performance in terms of radiation pressure noise. And the way we get around that is we have high power lasers and we try to suspend heavy optics. And this is a little bit like a Heisenberg uncertainty problem. It's exactly the same problem, that you can't measure position and momentum of an object or an electron, for example, arbitrarily accurate, because as you try to measure the position more accurately, you affect the velocity or the momentum of the particle. So it is a quantum limited detector. And then we also have thermal noise, the fact that these mirrors are not at low temperature, they're at room temperature. So what we find is this agitation in the front surface of the mirrors that you can see there on the right hand side, the suspension fibers that are used to support the mirror. That thermal agitation gives rise to displacement noise, and displacement noise essentially can mask the signal that we're looking for. So what we try to do is we try to make these detectors out of the purest materials possible. So we make the mirrors out of fused silica, high purity optical quality glass. We suspend the final stage on glass, and that's in order to make these resonances. These are the sort of frequencies at which these pendulum would like to sort of swing backwards and forwards, or the if you sort of pluck one of those strings of the suspension, it will vibrate just like a violin mode or guitar string. So these are the modes that you see in that the pendulum mode and an internal mode of the mirror or the suspension. We make the materials very high quality factor, and that puts lots of energy into the resonance, which means that off resonance thermal noise is actually reduced. And that's the way that we operate our detectors. This just shows you some of the work that we've done in Glasgow in terms of hanging mirror suspension. This is one of the activities that I lead in the UK. Is we build the technology for the LIGO detectors for hanging their mirror suspensions. This is the geo suspension, and then we upscale that to, rather than a sort of 10 kilogram optic or a little bit less than 10 kilograms, LIGO uses 40 kilograms. So there's the 40 kilogram optic, and there's one of the masses above. And there's another mass above. Remember, we have a cascaded pendulum suspension. And then this is the object that actually senses the laser beam. And then 4 kilometers away, there's another mirror. And all of that final stage that you see there is made out of glass. So we have glass fibers supporting this 40 kilogram mirror. Of course, we've made detections, and you'll have heard about that. So I'll just sort of skirt through some of the exciting science that you can get from these sources. Of course, this made huge news when the detection was announced. Since then, we've uncovered many more secrets of the universe, many more binary black holes and neutron stars and neutron star black hole binaries. But this was the original signal. This is called GW 150914, so measured back in 2015 in September. So this is what we call the time domain signal, and this is the strain. This is h as a function of time. So you can see this time's very short. It's only about 0.1, 0.15 of a second. So we just capture that last little in spiral of the binary black hole. So these were two binary black holes that were observed. So this is the time domain signal. What we can do is we can actually turn this and look at the what we call the frequency domain by taking something called a Fourier transform. And here we're just seeing noise. So when you look at that, you just see this is from 30 hertz up to 512 hertz. So this is converting time into frequency. And we don't see a lot. We just see sort of noise in blue, not much energy in that signal. And then as we go along, then we can do the next box. Still not a lot more. And then likewise, we can continue. And then as we sort of uncover, we start to see that, well, you can see here the time domain signal is growing, and then indeed you can see the power growing in the signal, and the frequency is increasing. So what's happening is those binary black holes, as they're spinning around, they're getting closer. That means that the gravitational interaction is getting stronger, but also because they're getting closer, they're speeding up. So you get this what we call a chirp signal, where the intensity of the signal increases, but also the frequency increases. So it's going up to about 300 hertz, and then it disappears, and that's when you coalesce into a single new black hole. And we saw that in both detectors. Both the Hanford and the Livingston detectors showed the same effect. A little bit time shifted by about 6 milliseconds, and that's because that tells you where the sources come from in the sky. So I think, again, where is the field going? Well, it's all about sort of combining gravitational wave detectors together with other electromagnetic telescopes or particle detectors. So for example, of course, we've got the two LIGO detectors and the Virgo detector. They've been working together as what we call a triple coincidence detector. Of course, CAGR will be coming online, and when we've got LIGO-India, then we'll have a whole network of gravitational wave detectors, and they'll see many, many more sources. So you can see here the first one, this is GW 150914. This was a heavy black hole binary. Then there were some other sources. This one here is, well, it's longer, it's almost 2 seconds in band. That means that was a lighter source, but still a binary black hole. These ones you can see somewhere between the heavy and the light, so that already by just looking at the length of time and the amplitude, you can get some information about the masses of the objects involved. And then this one here is a really interesting one. You can just about see there is a little ripple here. This was a binary neutron star, so what we call GW 170817. So this was two 1.4 solar mass objects rotating around one another, and that means they stay in band a long time because they're low mass. So what we got was about 200 seconds of observation, and when that object coalesced, it actually came along with it a small pulse of electromagnetic radiation, which was picked up by some of the astronomical telescopes around the world. And this is really exciting, this field of multi-messenger astronomy, because you're using different messengers to understand the origin of the universe. So for example, with the neutron star binary, because we saw gravity and electromagnetic counterparts, we could actually measure the speed of gravity. So very exciting observations. And that's, of course, where we are at the moment. So this is masses of objects detected by LIGO. So these are black holes. These are some of our neutron stars. And this is a sort of heavy object where it combined a black hole and probably a neutron star to develop a slightly heavier object. So there's a lot of detail in the whole spectrum. Just to show, it is a sort of large international collaboration. So we have this LIGO scientific collaboration, about 1,500 members, and it does take collaboration to build these detectors. Just to sort of highlight a couple of things with our international collaboration with India, this is funded under a Newton Barbar Award through the Science and Technology Facilities Council, and this is building together capacity between UK institutes and also Indian institutes. So this has been going for a number of years now, and we're working in a number of areas. So we work on skills training. It's about sort of building skills necessary to run a detector in India. So that involves a number of activities. So we've been doing work with laser stabilization, and that's between ISA Pune, Sheffield, Glasgow. IUCA has been doing a lot of work in building a lab to do suspension control and optical measurements with small cavities. We work with TFR Hyderabad, and that's on coating work. So we measure the coatings on the optical mirrors to make sure that they're going to be sufficient quality, both in terms of reflectivity, but also in terms of their thermal noise, or what we call mechanical loss. IUCA has been very active in organizing workshops. So we have some interferometer simulation tool called Finesse. So been doing some sort of online workshops around sort of design of optical cavities. We hosted recently a build a detector workshop. So that was very successful. It involves sort of live Q&A and lecture sessions by experts in the field around the world, and also Indian students. And what happened was we got the students into groups, and they designed and built their own gravitational wave detector. And some of those technologies were very interested, and we're actually taking a look at them for possible developments that could be put into LIGO in future. So that was really successful, and we're going to be running that again as a similar format. We've done a lot of outreach in STEM, so we've done various book launches. We have this game called Space Time Quest, which has now been translated into Hindi. So this is about, again, it's a game about building your own gravitational wave detector. So do go along and download that. It's quite nice. It gives you a way of understanding about sort of budgets and constraints of what you want to build for your detector. We have little interferometers called LIGO in your hands, and that teaches you about how interferometers work and some of the noise sources and what the signals look like. And then we've done quite a lot of development of leaflets showing about gravitational waves in the local dialect where the detector is going to be located. And we've just recently launched a pop-up book. So there's a lot of really exciting, nice work going on. And again, it requires this international collaboration to build this community, but also develop the technology. So this is a nice way to think about entrepreneurial work, because of course, pushing the limits of technology, we find that there's lots of application for applied spin-offs. So certainly in gravitational wave astronomy, we find lots of areas where we're pushing into different activities. So some of the work we do on bonding glassy materials, like in our mirror suspensions, we use that in bonding of laser crystals and laser components. We do a lot of control automation, so that finds applications in more efficient lift motor control. We're very good at isolating suspensions, but if you shape stem cells, then you can get them to differentiate into different materials. So we have one of our collaborators in Strathclyde is working on stem cell differentiation. We're working on efficient gas sensors, so CO2 and carbon monoxide sensors, using interferometry to look at the weathering of sandstone, using some of our data analysis techniques to look at eyes and retinal scans of the eye to work out which is you know, a good image of an eye, and how do you sort of stitch together multiple images. And then of course high coating damage thresholds for laser usage. So of course we have very high power laser operating in the LIGO cavity. So we find that when we get dust on the optic, we need optics that are actually quite robust against that kind of laser threshold damage. And then this one I'll talk a little bit more about. This is one of my activities that I've spun off. So I have another research group in Glasgow, which are building precision MEMS gravity sensors. So let me talk a little bit about that applied research in the last sort of 9 or 10 minutes. So this is a microelectromechanical sensor or MEMS device, and it's called a MEMS gravimeter. And a gravimeter is essentially, it's an accelerometer, so it's quite similar to what's in your phone, but just much more sensitive. So your phone accelerometer can't tell if there's a tunnel under the ground, whereas this device, this MEMS gravimeter, can actually work out if there's the hidden tunnels under the ground. And what it does is it's essentially a small silicon proof mass sitting in a hermetically sealed package, and that proof mass is suspended by these 4 flexures, and it's essentially a mass on a spring. So as we sort of move this object around, we can sense local gravity, or little g. And if there's a tunnel under the ground or missing mass under the ground, we find that little g is a bit smaller, and that's because little g, or the local acceleration of gravity, is determined by what's pulling down under your feet, and it's predominantly the Earth. But actually, if you've got local variations of mass distribution, you find that there are actually variations in local gravity. So we use that to actually sort of predict what's under our feet. And there's a number of areas of application. Oil and gas prospecting, that's still quite an active area. It's been using gravity sensors or gravimeters for many decades. And again, you're looking for changes in gravity that could indicate changes in geology that could host oil or gas. Of course, some of the oil and gas companies now are actually switching over and looking at carbon capture and utilization. And again, gravimetry will find a use there. Volcanology and environmental monitoring. So we have an array of our gravimeters on Mount Etna. And again, we can look at magma buildup in volcanoes. You can look at water courses. You can look at water under the ground where it's sitting. So there's a lot of applications in environmental monitoring. Defense and security, of course, there's opportunities looking at hidden tunnels, hidden compounds, underwater monitoring. These are application areas. Of course, navigation. So if you have an accelerometer and you integrate twice, then you can turn acceleration into position. And when you're GPS denied, so maybe you're going in a tunnel and you don't have GPS, well, actually, if you integrate acceleration, you can still get a fix of your position. And of course, if you're in a submarine, this can also be quite useful. And then, of course, civil engineering, so looking for sinkholes or mine shafts. So there's a lot of application areas there also. What's been really limiting is that there's current gravity sensors are quite expensive, which means you typically only have one of them. So what we've been trying to do is take some of the technology from the gravitational wave community, apply it to this gravimetry, but develop a MEMS system. And that MEMS system is much smaller, lighter, cheaper. So it means that you can do array-based gravity sensing. These are some of the things that we're looking at, some of our user cases. So here is a mass. This could be an underwater application where we've got something on the bottom of the sea and maybe a ship going over the top. And you see that the gravity signal as the object goes over, then it changes. So you can use this as a way of monitoring ships. Other things about ships, of course, which are interesting. The signals are quite small. They're about 10 billionths of the Earth's gravity, or 100 billionths of the Earth gravity. So you need very sensitive, stable devices. So it's quite an experimental challenge, but not unlike gravitational wave astronomy. Then we have another project that's ongoing where we're looking at the monitoring dams. So this is a dam not far from Glasgow. It was about 60 miles from Glasgow in the Scottish Highlands called Cruachan. And what we've been doing is we've been modeling gravity around the dam, and we can use that to infer water level and water ingress into the local dam. So we've got a geophysical map of the local area, terrain map, and turning that terrain map into local gravity measurements. So we've been getting out doing lots of field trials. This is the device. So here's the MEMS sensor. So this is the proof mass. You can just about see the flexures here. There's 4 of them. So this is a proof mass in its down position, measuring vertical gravity. There's a capacitive set of electrodes that are patterned using standard micro and nanofabrication techniques. Just about see them there actually on the right hand side. So these are sort of essentially comb electrodes. So this is metal electrodes on the surface of silicon. And then we drive those electrodes with voltage signals. And then we have a pickup plate here, which picks up the voltage. And that allows us to work out the vertical height of that to about 50 picometers. And then as that as that mass moves up and down due to gravity changes or seismic changes, then what we see is a time varying gravity signal, and we can turn that into a local acceleration measurement. So this is the device as it stands at the moment. So we've been doing a lot of work trying to get this into a small form factor device that can go out doing field trials. So we've had to build this sort of custom electronics. So we use a commercial field programmable gate array, but then we have a set of temperature and MEMS control electronics that we've built ourselves. So this gives you a little bit of information about the sensor as it currently stands. So we've got a number of sensor channels. So these are the capacitive sensor channels. So we read two MEMS channels, and we also have the option of reading another couple of channels to do stabilization. We've got 6 temperature channels. We've got 4 heaters because we have to control the temperature of these devices to about 0.1 of a millikelvin in order not to see changes in our spring affecting gravity. We've got an inclinometer, which measures tilt. We've got humidity and pressure sensor. When we put it on the side of a volcano, we have to have remote leveling because the volcano tilts. So we have stepper motors that we can remotely control. We have this custom graphical user interface that we've built. So this is the temperature monitor channels. And now we've got internal batteries and also Bluetooth control. So we don't actually have to have any wires going to the sensor. And that makes the surveying much, much easier. This shows you the performance of the device. So it is one of the best MEMS gravimeters out there. So you'll know about the tides. So water tides, of course, are due to the tidal potential of the moon and the sun. Well, actually, we also see tides in the solid earth. So the tidal potential of the moon and sun also stretches and shrinks the earth by about 20 centimeters at Glasgow. And that means that twice a day we move closer or further away from the center of the earth. And that means that our local acceleration of gravity changes. And we call this the earth tides. So we were the first device, MEMS device, to monitor earth tides. And you can see here the black is the theoretical and the gray is our actual sensor measurements. And they get smaller and bigger depending on the phase of the moon and the sun. And you can see sometimes it gets a bit noisy, and that's when a storm passes through. But you can see about a month of data there where we've monitored some wonderful earth tides. This is where we are at the moment with field trials. Well, not at the moment because it's snowing outside here in Glasgow, but we'll get back into field trials fairly soon. But we're going around the university. So there's some tunnels under the university here in our cloisters. We're going over bridges. So bridges, because there's no mass under the bridge, then you find that gravity is a little bit weaker. We're doing trials in Birmingham. And this is an interesting one. So this is, again, a comparison with your phone. So this is going up from the bottom of our physics building to the top of our physics building. And what you see there is each floor. So what we're seeing there is as you move away from the center of the earth by going up in a lift, then gravity gets weaker. Now your iPhone or your Android phone won't tell you that because the accelerometer is not sensitive enough. But our MEMS device can actually see those changes in gravity. So it really is an exquisitely sensitive device. And we're now just sort of really working hard on the commercialization aspect of the project. So it's a nice example of where we sort of spun off gravitational wave technology into a more applied commercial opportunity. So I think I'll finish there. I'll be online and very happy to take questions either about the fundamental science or the applied spin-offs. So thank you very much. All right, thank you very much. Well, I hope you enjoyed the presentation. I was just looking at the chat window on the YouTube live. So I see there's one question that was coming up. So I'll sort of address that question. If there's any more questions, then please keep them coming into the chat window. So there's a question from Harsh Prajapati. So high resonance frequency is working on orbits of planets and other celestial bodies in our solar system. Well, that one really is about gravity. So in the talk, I mentioned the one slide on general relativity. And of course, that's our current best theory of gravity. And the way that any theory works in physics is that you come up with some prediction, and then you need to do tests against that theory. So indeed, general relativity has passed all of those tests extremely well. It really is a wonderful theory. So what are some of those tests? Well, in the talk, we already heard about the fact that the speed of gravity and the speed of light are the same. Now, that's a prediction from general relativity. And the fact that that is really born to be a measured property from our LIGO detections means that we believe that general relativity is a good theory of gravity. But there's other tests as well. So, for example, things like when there's a solar eclipse, then what you find is that starlight or photons get bent as they travel and traverse through this curved space-time. And again, that's a predictable sort of event. It's quite a difficult one to measure, but it's been done. It's been done optically a few times, but that's a very difficult experiment. It's easier to do with radio waves. But again, that's proof further that general relativity is a good theory of gravity. So central to this idea is that the celestial mechanics of our universe is defined by gravity. So when you have objects the size of planets or asteroids or stars or black holes, then they are really defined by their gravitational interaction. Not like most things on Earth. So for example, in the talk, I spoke about MEMS gravimeters, and there we're always fighting against forces that are sort of equivalent to gravity. So things like electrostatics become a big challenge. But certainly for planets, they're large enough and neutral potential that gravity is the dominant force. So the beautiful mechanics that we see, the celestial mechanics, is really defined by the gravitational interaction. Let's see. Let me take any more questions. I see Kieran Mehta. What governed the choice of FPGAs over, say, GPUs? So that's a good question. So this is in our MEMS gravimeters. So of course, we had to make the decision, how do we actually control the instrumentation? How do we control and read out the MEMS device? Really, an FPGA was chosen because it was perhaps an easier system to get entry level into to start with. We'd done some work prior to that on microcontrollers. So we built an early system that was based around a PIC microcontroller. So it felt like that there's actually a natural sort of step over to go to an FPGA. What we're really looking for is we're looking for small form factor systems. So the FPGA is a good example of that. We can actually make that very easily into a chip-based system. So we've got our own custom FPGA board now. So we just buy in the sort of 1/2" by 1/2" chips, and we actually populate them ourselves on the board. That's much more difficult to do with a graphical processor unit. Plus the coding that we need to actually kind of work with the system. So we have to do a lot of sort of filtering of systems, and there's naturally some very well-defined and efficient filter blocks that we can use and take straight from both our FPGA work and our earlier microcontroller work. It's a good thought, though. It's not out of the question that we'll use those in the future. And actually, GPUs are an example where they're actually used a lot in gravitational wave digital signal processing. So using the sort of power of those systems is very important for data analysis. But for our applications, they're a little bit less power hungry. We require sort of fairly fast update rates are about a megahertz, but that really isn't any problem for an FPGA. Let's see any more questions. Yes, good question from Rajpal Singh. Gravitational waves are measured at what frequency? Well, actually, they're measured at many frequencies, but in LIGO, it's a ground-based detector. And the LIGO detector works really well between about 20, 30 hertz up to a few kilohertz. So you might remember the plot that I showed where it's the time series of the gravitational wave, and it was also the frequency. So in that plot, you could see that the frequency started at about 30 hertz and went up to around a few hundred hertz. And those are the sort of last spirals of the binary black hole system. So for LIGO, we observe in that band, but it doesn't mean there's not gravitational waves at different frequencies. So if you move to lower frequencies, there's a big push now for making space-based gravitational wave detectors. Certainly we have an instrument under development called LISA, and that stands for Laser Interferometer Space Antenna. And that's going to be an orbiting system that has arm lengths of a few million kilometers, and that allows us to measure much lower frequency gravitational waves. So that will work typically down to a few millihertz or slightly less than a millihertz up to 0.1 of a hertz. And then even lower than that, so when you get sort of supermassive black holes, then you can get even lower frequency signals. So we're looking at the very sort of long kind of duration signals as these objects sort of orbit one another. And that's the domain of what we call pulsar timing. So if we know that there's neutron stars, and of course we observe a neutron star with LIGO. So we see neutron stars, and they're like little lighthouses, and they're beaming out electromagnetic radiation all the time. So they're very accurate clocks. So they're like little ticks of a clock. And if you look at enough neutron stars with radio telescopes, you can look at how regular the ticks are from those objects. And if a gravitational wave from one of these supermassive black holes passes through, then it actually changes the local coordinate separation of space-time. So the ticks get perturbed by a little bit. So if you look at maybe 40, 50 neutron stars as accurate clocks, then what you can see is you can actually in principle, detect these gravitational waves through timing of pulsars. So there's a big international collaboration to build what we call the International Pulsar Timing Array, and they've been observing. It's not exactly clear when they'll actually see a first detection, possibly a few years' time when they gather enough data. But one of the challenges is they have to observe for about sort of 5 to 10 years, and it's not exactly clear how stable pulsars are over those extremely long time periods. And then finally, the other really low frequency bands, right the way down to the 1 over the age of the frequency is 1 over the age of the universe, and that's related to the cosmic microwave background. So you might have seen in your studies that when we look at the relic of the Big Bang, we see imprinted on the background about as far as we can see back in the electromagnetic spectrum is the cosmic microwave background. And that's got sort of small fluctuations of temperature on it, which we believe seed the formation of galaxies. Well, we also think that there's actually an imprint, as well as the electromagnetic signature, there's actually a gravitational wave signature imprinted. So there's detectors down at the South Pole, and they're called BICEP. And what they're doing is they're actually looking for these sort of very, very subtle signatures in the cosmic microwave background. So indeed, just like electromagnetic radiation goes from everything from radio waves through optical, infrared, ultraviolet, X-ray, gamma ray, we have a whole sort of spectrum of gravitational waves as well, from the very low frequency up to the very high frequency. And it's just that in the LIGO detector, we see that really small kind of fraction of a second due to these sort of coalescing binary systems. All right, let's take any more questions. So from Pritam Gamming, optical counterpart of neutron star gravitational wave, just after how much time of direct detection? Not exactly quite sure what the question is there, but let me make some more sort of comments about that. So in terms of the optical counterpart, once the gravitational wave was detected, there was a really big push for every sort of optical telescope, electromagnetic telescope, really, to sort of point in roughly the location where we thought that the gravitational wave had come from, and that's quite a big patch of sky. So with the two LIGO detectors, you're looking at several hundred square degrees. So the optical telescopes were sort of tiling this sort of really big square section of sky. And it was a few days later that the first sort of observations were coming in from the sort of not the really big telescopes, but the sort of maybe a couple of meter class telescope, which could actually sort of tile the sky fast enough. And then once the object had been detected, then it could be sort of observed in great detail and actually followed up with many other electromagnetic frequency bands. Okay, good. Let me see. There's a question here about why micromachine silicon as a proof mass and factors limiting the sensitivity. Yep, great question. So why do we choose silicon for the MEMS? Well, really because it's a standard micro nano fabrication material. If you go into any clean room, then the standard tools are set up to etch silicon. Now they're set up to etch silicon through quite a deep layer. So our wafers are around 240 microns thick. So we can actually etch silicon through that depth. It's a good material to work with because it's actually fairly strong. It's actually not quite as strong as the fused silica that we use in gravitational wave detector suspensions. But fused silica is much harder to sort of work with and etch in what we call an anisotropic way. So if you remember those pictures of the MEMS, you'll see that there's the structures that we need to etch out from sort of top down. So there's like the proof mass and these very thin sort of 10 to 11 micron flexures. So we have to do this extremely anisotropic etch. So silicon etch tools are very well set up to do that. So that's the choice of silicon. And what limits the present sensitivity? Well, that's a long list of things, but let me give you a sort of two or three of the main ones. So we always get limited by readout noise. So when you look at this device, you're trying to measure kind of motions that are sort of maybe 10 picometers. So I agree that is huge compared to a gravitational wave sort of detection that's needed, where we're looking at 10 to minus 18 of a meter. However, this is a very small scale system. So measuring 10 picometers is a little bit of a challenge. So our capacitive sensor has noise on it, and that's due to a variety of reasons. So one is we see drive, as we sort of drive these electrodes to read out the position, we see a fluctuating voltage noise. So that comes from our sine wave drive, and that sort of leaks through. If we perfectly balance the two capacitors in the MEMS, then we're actually quite insensitive to that, but we never quite perfectly balance. We also see noise on the signal chain. So any of the electronics that we use to turn our current into a voltage, they have electronic noise, and there's a variety of sources of that noise, but the dominant one is thermal noise, because the electronic components are run at room temperature. So they have thermal agitation noise. Again, just like we see in gravitational wave detectors with the suspension thermal noise, this is electronic thermal noise. And then also the ADCs, the analog to digital converters that read in the signal, they're also sensitive they also have what we call quantization noise. Because anytime you take a signal and you take it from the time domain, so a continuous signal, so our MEMS signal is continuous voltage, and you digitize it. So when you digitize it, you make it discrete. And that digitization, because you have to sort of put the voltage levels into specific steps, then you add noise, and we call that quantization noise. So our 8 analog to digital converters have noise. Then some other sources that give us long-term fluctuations, then thermal fluctuations are a challenge. So the MEMS spring is made out of silicon, and that's got a thermal expansion coefficient and a variation it's shown as modulus with temperature. So what we see is long-term drift, and we call that noise as well at low frequency. And then we also see seismic noise. Now, for many people, seismic noise is a signal, but for us, seismic noise is something we'd like to get rid of. It's a noise source. So what we do is we actually filter the data, and our biggest source of seismic noise is what we call the microseismic peak, and that's a peak in the seismic spectrum that is due to ocean waves crashing onto the continental shelf and sort of driving vertical oscillations of the ground. So those are sort of 3 of the key noise sources. I could keep going, but I think with time, then let's see if we've got any more questions also. But thank you very much for that one. Okay, another, was miniaturization driven by noise concerns or some other form factor related goals? It's really driven by the fact that in order to get gravity sensors portable, with the view of either carrying them around in the field, making them as small is quite beneficial. We also wanted to potentially put them onto a drone. So again, that meant small form factor. But I also draw an interesting parallel, and it was the work of, you might have heard of the work of John Harrison, who was a clockmaker, an English clockmaker. And of course, he's sort of really solved the longitude problem, which was how do you carry a clock on board a ship and measure longitude. And of course, to measure longitude, you have to measure your local time, which is easy to measure, but you have to measure the time back home. So in the case of, let's say you started from Greenwich in London, then if you sail across to Jamaica, then you have to know the time in London in order to work out your longitude. And the way that the longitude prize was solved was Harrison made marine chronometers or clocks. And he started off building these very large systems, and they were good, but they weren't very stable. And the systems that actually won the longitude prize for him were actually quite small form factor systems. And he always put that down to the fact that small form factor systems, well, one, you could actually control their environment much easier, and I think we find the same here. But the other thing is that you try to store more sort of mechanical energy in the spring of the clock rather than sort of the surroundings. So for Harrison, miniaturization was key, and I think for us as well, as you make the system smaller, then you get less sensitive to environmental noise. But you have to be a little bit careful, because if you make it too small, then you get limited by thermal noise, because as we make our MEMS smaller and smaller, the mass gets smaller and smaller, and at some point your thermal and your electrostatic forces start to dominate. So it's a little bit of a trade-off. You can't make it as small as you'd like. We're about at the limit where thermal noise is about at the 1 to 5 microgal, which is about our base sensitivity. Okay, excellent. And then, yeah, another question, which is a good one. So 10 picometers in low frequency is quite challenging. Yeah, it is. And one of our biggest challenges is the long-term stability. So when we monitor earth tides, and again, not many MEMS devices out there have sufficient either sensitivity or stability. And I think the key here is stability. So we find that not many MEMS systems have the stability to actually monitor the local variations of gravity. So as I said in the talk, twice a day, the local acceleration of gravity varies due to the tides of the moon and the sun. And those are really quite subtle effects. And one of the real challenges is when you put these MEMS devices outside, then you find that the thermal variation can cause sort of displacement of the proof mass that can completely sort of swamp the tide signal. So that's one of our biggest challenges, and that's why we work so hard in putting multiple thermal layers of control around the MEMS device. So we've got the outer enclosure, and we stabilize that to typically about 1 degree. variation in, so one degree centigrade or 1 Kelvin. And then we have an outer box, which we control. We have an inner box we control, and we have the MEMS package itself, which we also thermally control. So at the MEMS package, the temperature is only changing by about 0.1 of a millikelvin, even though the outside temperature might change by 10 degrees as you take it outside or into the sun. So that's a real challenge, and that's one of the big challenges for us, is getting devices from the lab out into the field. And in order to make the commercialization step to say that these devices really work well as MEMS gravimeters, then it's absolutely essential that we actually can do these field trials. So we're going to continue doing field trials, what we're really doing is we're taking the devices outside, we're doing some gravity surveys over known areas and showing that these systems can really perform as well as the current benchmark systems, which might be something like a Syntrex CG5. And the whole goal of this work is to make these MEMS gravimeters about 10 times cheaper than current devices, and that allows you to have 10 times more devices. So I think I'll finish there. Thank you everybody for the excellent questions. They were really good and always fun to respond to. I really hope you enjoy the rest of your science day. It's always a pleasure sort of talking. Of course, I would have liked to be there in person, but current travel doesn't quite allow that. Although I'm very pleased to say that the technology that we have from the LIGO-India colleagues is excellent and allows us to take part in this work. So thank you everybody for making this happen and giving us such interesting questions.
Thank you, Giles, for connecting with us and for this wonderful overview of the Newton-Bhabha collaboration. Next up in today's program, we have a fun session called Behind the Scenes, where students from all across the country and all across the world take us on gravitational wave science campus tours. First, we visit the IIT Gandhinagar campus with Radhika Gandhi, followed by Swarnim Shirke from Ayuka, who's taking us on a campus tour. Next, we fly to the Clayton campus of Monash University in Melbourne, Australia, with Isabel Romero-Shaw. Finally, we take a tour of the Anton Pannekoek Institute for Astronomy in Amsterdam, Netherlands, with Devarshi Chaudhary. Enjoy.
Exactly a century ago, in 1921, Anton Pannekoek founded our institute, now located on the modern Science Park campus in our country's creative center. API has grown to an international community of about 100 members, with a leading role in the push for diversity and inclusion. We have close connections to our Nova sister institutes and national research institutes on and off campus, especially Astron, ESFRON, and NICHEF. Research at API primarily revolves around the births and deaths of stars and planets and on compact objects. From our strength in classical astronomy, we've expanded into astroparticle physics via the GRAPPA initiative and into exoplanets via the Oranges initiative, with colleagues in all other sciences. In this atmosphere, our young faculty and junior members thrive, winning grants and prizes for their frontier work while having a good eye for each other's well-being. Our teaching focuses on the strong astronomy component of the Amsterdam-wide joint bachelor's and master's degrees in physics and astronomy and provides solid grounding in theory, computation and observation. The latter starts in our flagship Anton Pannekoek Observatory and culminates in projects in professional observatories such as LOFA and La Palma. We also share our excitement about the wonders of the universe with the wider Amsterdam area community using live and online events, again with a particular focus on its rich diversity.
After a tour of the Gravitational Wave Science Institutes from all over the world, we are now going to connect with those who are living close to the LIGO-India site in Hingoli district of Maharashtra. Next up we have Professor Varun Bhalerao from IIT Bombay speaking in Marathi on खगोल शास्त्र आणि तंत्रज्ञान. आता आपण मुंबई IIT मधील वरुण भालेरावांकडे जाऊयात. ते आपल्याशी खगोलशास्त्र आणि तंत्रज्ञान बद्दल बोलणार आहेत.
नमस्कार मंडळी, मी वरुण भालेराव. मी मुंबईत IIT मध्ये आहे आणि आज मी तुमच्या बरोबर बोलणार आहे खगोलशास्त्र आणि तंत्रज्ञान या विषयावर. तर आज 28 फेब्रुवारी राष्ट्रीय विज्ञान दिवस. पण हा विज्ञान दिवस आपण का साजरा करतो त्याचं कारण एक तुम्ही ऐकलंच असेल, त्याच्याकडे येऊ आपण. पण त्याही आधी आपण खरं सुरुवात करूयात आपल्या संविधानाने. तर आपण शाळेत शिकलेलो असतो, आपल्याला सगळ्यांना मूलभूत हक्क आहेत, काही अधिकार आहेत आणि आपल्याला काही मूलभूत कर्तव्य पण आहेत. तर त्यातलंच एक हे खरं तर विज्ञाननिष्ठ दृष्टिकोन किंवा ज्याला सायंटिफिक टेम्पर असं म्हणतो, हे आपल्या सगळ्यांची जबाबदारी आहे आपल्या संविधानाप्रमाणे. आणि म्हणून विज्ञान हे प्रत्येक भारतीयाच्या आयुष्यात अतिशय महत्त्वाचं आहे. याचा पहिला तुम्हाला लगेच मी एक होमवर्क देतो की विज्ञान म्हणल्यावर स्वतः शोध घेणं फार महत्त्वाचं असतं. तुम्ही सगळे हे टॉक ऑनलाईन बघताय, आज हे व्याख्यान ऑनलाईन ऐकताय, तर आपलं संविधान ऑनलाईन उपलब्ध आहे. जा, बघा आणि वाचून बघा. हा भाग 4 जो मी म्हणलोय, खरंच त्याच्यात असं लिहिलं आहे का? आता विज्ञान महत्वाचं आहे, पण 28 फेब्रुवारी हा मुहूर्त कशामुळे महत्वाचा? तर ह्याची सुरुवात जवळजवळ 100 वर्षापूर्वी CV रमन यांच्यापासून होते. स्वातंत्र्याच्याही 20 वर्ष आधी त्यांनी त्यांचं काम चालू होतं, त्यांचा रिसर्च चालू होता. वेगवेगळ्या गोष्टींबद्दल त्यांनी खूप विविध गोष्टींमध्ये काम केलं आणि हे इथे तुम्हाला त्यांचं जे इक्विपमेंट दिसतंय त्यातनं त्याचा वापर करून त्यांनी रमन इफेक्ट नावाचा प्रकाशाबद्दलचा एक शोध लावला. रमन इफेक्ट काय ह्याच्यात मी आज जाणार नाही, पण तो शोध 28 फेब्रुवारीला लागला होता, म्हणून आज विज्ञान दिवस. आता विज्ञान दिवस हा उपक्रम दरवर्षी आपलं केंद्र सरकार साजरा करतं आणि दरवर्षी त्याला एक विषय, एक थीम दिलेली असते. ह्या वर्षीची विज्ञान दिवसाची थीम आहे विज्ञान आणि तंत्रज्ञान. तर आज आपण पुढचा साधारण तासभर ह्याच विषयावर गप्पा मारूया. विज्ञान आणि तंत्रज्ञान म्हणल्यावर आपण म्हणू पहिलं रमन इफेक्टनी आपण सुरू केलं, त्याचा तंत्रज्ञानाशी काय त्याचा संबंध. तर आज रमन इफेक्ट हा जो 100 वर्षापूर्वी प्रकाशाबद्दल काहीतरी एक कुतूहल असल्यामुळे त्यांनी शोध लावला होता, तो खूप ठिकाणी वापरला जातो. जसं तुम्ही जर औषधं बघितलीत, एखादं पॅक केलेलं औषध तुमच्याकडे आलं आणि त्याच्यात खरंच आतमध्ये काय आहे हे जर तुम्हाला जाणून घ्यायचं असलं, तर रमन इफेक्ट वापरून असे इक्विपमेंट असे काही तुम्हाला वापरता येतात, ज्यांनी त्या औषधाला हात न लावता किंवा कुठल्याही पदार्थाला हात न लावता त्याच्यात कुठले मॉलिक्युल्स आहेत हे आपल्याला कळू शकतं. आणि असे वेगवेगळे त्याचे वापर जे केले जातात ते अगदी म्हणजे स्मगलिंगमध्ये सुद्धा काय कोणी लपवण्याचा प्रयत्न करतंय का? किंवा औषधांची चाचणी करण्यासाठी त्यांची क्वालिटी चांगली आहे का बघण्यासाठी ह्या सगळ्याचा वापर केला जातो. सो विज्ञान आणि तंत्रज्ञान हे शब्द खूप वेळा एकत्र घेतले जातात कारण ते कायमच जोडलेले आहेत एकमेकांशी. माझा स्वतःचा अभ्यासाचा विषय आहे खगोलशास्त्र. त्यामुळे आज आणि आपण आयुकाच्या सायन्स डे मध्ये आहोत, आयुकाच्या विज्ञान दिवसाच्या कार्यक्रमात आहोत. त्यामुळे निश्चितच आपण खगोलशास्त्राबद्दल बरंच काही बोलणार आहोत. तर मी सुरुवात करतो खगोलशास्त्रातील तंत्रज्ञानाने. खगोलशास्त्राचा अभ्यास करण्यासाठी तंत्रज्ञान का गरजेचं आहे? तर साहजिकच भारतीय ह्याचा मी तुम्हाला कॉन्टेक्स्ट देईन, त्याचे तुम्हाला उदाहरणं देईन. तर इथे 3 दुर्बिणी आहेत. त्यातली एकही तुम्ही दुर्बीण म्हणल्यावर जे मनात येतं त्यासारखी दिसत नाही. पण ह्या 3 दुर्बिणींवर मी काम केलंय आणि करतो. त्यामुळे मी ह्यांची उदाहरणं देऊन विज्ञान तंत्रज्ञान एकत्र कसं येतं खगोलशास्त्रात ह्याच्याबद्दल आज सांगणार आहे. हा पहिला डावीकडचा जो फोटो आहे ह्याच्यात एक ऑप्टिकल टेलिस्कोप म्हणजे आपण साधारण दुर्बीण म्हणल्यावर जी अशी विचार करतो त्याचाच मोठा भाऊ म्हणू आपण. हा 70 सेंटीमीटर व्यासाची एक ग्रोथ इंडिया म्हणून ऑप्टिकल दुर्बीण आहे. त्याच्याबद्दल पहिलं बोलू. मग ॲस्ट्रोसॅट म्हणून भारतीय उपग्रह आहे ज्याच्यात 5 वेगवेगळ्या प्रकारच्या दुर्बिणी आहेत. जो 2015 मध्ये ज्याचं प्रक्षेपण झालं त्याच्याबद्दल बोलू. आणि आता आम्ही एक नवीन उपक्रम सुरू करतोय इस्रोच्या सहाय्याने आणि बाकी बऱ्याच संस्थांच्या सहाय्याने. आम्ही दक्ष नावाचे 2 उपग्रह बनवायसाठी आता काम करतोय. प्रपोजल आमचं चालू आहे. आणि ह्या 3 गोष्टींमध्ये तंत्रज्ञान कुठे-कुठे येतं आणि कसं येतं ह्याबद्दल आपण बोलूया. तर सुरुवात करूयात ग्रोथ इंडिया टेलिस्कोप बरोबर. हा इथे तुम्हाला जो डोम दिसतोय खाली तो आमचा लडाखचा ग्रोथ इंडिया टेलिस्कोप. हानले म्हणून एका ठिकाणी माउंट सरस्वती नावाच्या डोंगरावर अतिशय सुंदर ठिकाणी हा टेलिस्कोप आहे. त्याचा डोम तुम्ही इथे बघताय. ही दुर्बीण आम्ही ह्याचं पहिलं काम सुरू झालं 2018 साली. तुम्हाला छान मागे आकाशगंगा दिसतेय आणि इथे पुढे बरेच दिवे चमकताना दिसतायत आणि हा डोम फिरताना दिसतोय. खरं तर जेव्हा रात्री दुर्बिणीचं काम चालू असतं तेव्हा अजिबात त्याच्यात एवढे ब्राईट दिवे लावून चालत नाही. कारण एवढे ब्राईट दिवे जर असले, एवढा जर प्रकाश असला तिथे, तर आम्हाला ज्या ताऱ्यांचे अभ्यास करायचे त्याचा प्रकाश इतका मंद असतो त्यासमोर, की आम्हाला त्याच्यात काहीच दिसणार नाही. मग इथे असं का चालू आहे? तर ह्याला कमिशनिंग असं म्हणतात, की दुर्बीण ज्या दिवशी पहिल्यांदा कार्यरत झाली, त्या दिवशी बाहेर एक कॅमेरा लावून ठेवला होता आणि त्यांनी हे सगळे फोटो घेऊन त्यातनं हे आता तुम्ही बघताय तो व्हिडिओ बनलाय. पण दुर्बीण पहिल्यांदी ज्याला फर्स्ट लाईट किंवा कमिशनिंग आम्ही म्हणतो, त्या भागातला हा व्हिडिओ आहे. आता ही दुर्बीण 2018 साली आम्ही इथे लावली. तर कशासाठी? काय अभ्यास करायचा आहे? ह्याच्यासाठी आपल्याला खगोलशास्त्रात थोडं अजून जाऊयात. आपण एरवी खगोलशास्त्र किंवा विश्वाचा जेव्हा विचार करतो, तेव्हा सहसा मनात असं येतं, की ग्रह-तारे ग्रह फिरतात सूर्याभोवती, पण त्या पलीकडे आकाशात गोष्टी फारशा बदलत नाहीत. आपण आपल्या जर जुन्या कथा वगैरेही बघितल्या तर ध्रुव ताऱ्याला अढळ पद म्हणलं जातं. कारण तो तर रात्रभर पण हलत नाही आकाशात आणि एकूण ब्रह्मांडात गोष्टी बदलत नाहीत, असा आपल्या मनात नेहमी विचार असतो. पण त्याचं खरं कारण जर बघितलं तर असं आहे, की आपलं आयुष्य हे 100 वर्ष. पण ब्रह्मांडात हे जे तारे जर बघितले तर त्यांचं आयुष्य काही लाख ते कित्येक कोटी वर्षांचं असतं. त्यामुळे आपल्या आयुष्यात या गोष्टी बदलताना फारशा दिसत नाहीत. पण तुम्ही जर कोट्यावधी ताऱ्यांचा अभ्यास एकत्र करू शकलात, तर तुम्हाला काहीतरी त्याच्यात बदल होताना दिसतील, की एखादा तारा कधीतरी बदलताना दिसेल. आता इथे तुम्हाला एक उदाहरण दाखवतो. इथे ही मध्ये एक दीर्घिका दिसतेय गॅलेक्सी आणि इथे हा जो लाल भाग मार्क केलाय तिथे लक्ष द्या. आपण आता सुरू करूयात इथे. इथे तारखाही लिहिलेल्या आहेत वरती. तर तिथे तुम्ही जर बघत राहिलात तर आधी काही तिथे दिसत नाहीये खास. दीर्घिकेचाच एक भाग आहे. पण आता अचानक एक नवीन स्रोत तिथे दिसायला लागलाय. आणि हा नवीन ताऱ्यासारखा दिसल्यामुळे ह्याला मराठी शब्द चक्क नवतारका असा आहे, नवीन तारा. तर हा नवीन तारा कशामुळे दिसला, तर तो तारा तिथे निर्माण झाला असं वाटतंय आणि अचानक तो परत त्याचा प्रकाश तीव्रता कमी पण होत गेली. इथे पुन्हा बघू झूम करून. हा एक नवीन तारा आला, त्याची तीव्रता खूप वाढली आणि मग नंतर आता हळूहळू तो पुन्हा मंद होत चाललाय आणि शेवटी तो गायब होऊन जाईल. ह्याला महाविस्फोट असं म्हणतात. सूर्यापेक्षा मोठे जर तारे घेतले, सूर्यापेक्षा 8-10 पट किंवा त्याहूनही मोठे, तर ह्या ताऱ्यांच्या आयुष्याच्या शेवटी एक मोठं एक्सप्लोजन होतं, एक विस्फोट होतो, ज्याला सुपरनोव्हा असं इंग्लिशमध्ये म्हणतात, महाविस्फोट. आणि त्यांनी निर्माण होणारा हा आकाशातला एक नवीन तारा. आपल्याकडे पूर्वीच्या काळातही हे तारे बघितले गेलेत. तुम्ही ह्याच्याबद्दलही ऑनलाईन व्याख्यानं ऐकू शकाल. एक बंगलोर प्लॅनेटोरियमच्या शैलजा मॅडमनी नुकतंच एक छान व्याख्यान दिलं होतं, की आपल्याकडे 1000 वर्षापूर्वी सुद्धा ह्याची कशी नोंद करण्यात आली होती आणि आपल्याकडेच नाही, जगभरात विविध ठिकाणी युरोपमध्ये याची नोंद होती, चायनात याची नोंद होती. असे हा नाही, हा विस्फोट नाही, हा 2015 साली झालाय, पण असे इतर आकाशात दिसलेले महाविस्फोट जे जवळ होते, त्यामुळे जास्ती ब्राईट होते, आपल्याला दिसू शकत होते. हे कसं होतं, तर हे जे मोठे तारे असतात, त्यांचं आयुष्य साधारण काही कोटी वर्ष असतं. पण त्या कोटी वर्षांच्या शेवटी त्याचा मध्यभाग जो असतो, तो काही सेकंदात फुटतो आणि त्यातनं मोठा तो अख्खा तारा जो सूर्यापेक्षा 10 पट वजनाचा आहे, त्याचा सुद्धा पूर्ण विस्फोट होऊन जातो आणि त्यांनी त्याची तीव्रता इतकी वाढते, की आपल्या अख्ख्या आकाशगंगेतनं जेवढा प्रकाश निर्माण होतो, तेवढा त्या एका ताऱ्याचा दिसू शकतो. आणि हे साधारण महिनाभर दिसतं आणि त्याच्यानंतर त्यातली ऊर्जा, म्हणजे जसा फटाका फुटल्यावर आपल्याला दिसावा, काही सेकंदांसाठी दिसतो आणि नंतर तो मंद होऊन दिसेनासा होतो, तसा हा प्रकार आहे. पण हा फटाका हा एक अख्ख्या सूर्यापेक्षा 10 पट वजनाच्या ताऱ्याचा विस्फोट असतो. असे आकाशात जे बदल होतात, त्याचा अभ्यास करायला आम्ही ग्रोथ इंडिया दुर्मिळ विशेषतः ह्याच्यासाठी आम्ही प्रस्थापित केली तिथे. आणि ह्याला टाईम डोमेन ॲस्ट्रोफिजिक्स म्हणतात. आणि अक्षरशः शब्दशः याचा अर्थ होतो, की आकाशात ज्या गोष्टी बदलतायत वेळेनुसार, त्यांचा अभ्यास करण्यासाठी जो विषय आहे, तो म्हणजे टाईम डोमेन ॲस्ट्रोफिजिक्स. आता अजूनही गोष्टी आहेत, जसं हा एक ॲस्टेरॉइड आहे. ॲस्टेरॉइड म्हणजे लघुग्रह जे सूर्याभोवती फिरत असतात. मोठा दगड. आणि असे ॲस्टेरॉइड्स इथे तुम्हाला दिसतंय ह्या हिरव्या गोलात, की एक ॲस्टेरॉइड खाली हलतोय. हे बाकी जे काळे डॉट आहेत ते सगळे तारे आहेत आणि त्या ताऱ्यांच्या समोरनं हा ॲस्टेरॉइड हलताना दिसतोय, कारण त्याची सूर्याभोवती कक्षा आहे, जशी पृथ्वीची आहे तशीच. या सगळ्या गोष्टींचा अभ्यास आम्ही ग्रोथ इंडिया टेलिस्कोपने करतो. आता पहिल्यांदा जेव्हा तुम्हाला एखादा महाविस्फोट झालाय असं कळतं, तुमच्या इतर सहकाऱ्यांकडनं तुम्हाला ईमेल येते किंवा फोन येतो किंवा मी आता इथे ऑफिसमध्ये बसलोय, माझा हा संगणक जो शेजारी आहे, त्या संगणकातनं चक्क आम्हाला फोन येतो, असं आम्ही त्याच्यात प्रोग्रॅमिंग केलेलं आहे. हे सगळं खगोलशास्त्रातलं तंत्रज्ञान, की कुणालाही असा जर डिटेक्ट झाला, असा जर शोध लागला, तर सगळे जगभरातले खगोलशास्त्रज्ञ एकमेकांना कळवतात. आणि पहिल्यांदा असं काही झालं, की रात्री 3 वाजता जरी असा फोन वाजला तुमचा, की तुम्ही लगेच अरे नवीन काहीतरी त्याच्यावर काम करायचंय, शोध घ्यायचा आहे म्हणून पटपट जातात. जेव्हा 10व्यांदा होतं, 12व्यांदा होतं, तेव्हा अरे 3 वाजले, झोपतो ना, असा विचार डोक्यात यायला लागतो. आणि जरी तुम्ही पूर्ण अगदी एन्थुसियास्टिकली गेलात, तरी तुमचं डोकं रात्री दरवेळी नीट चालेलच असं नाही. आपल्याला वैज्ञानिकांचं काम कुठे आहे, तर त्यांनी क्रिएटिव्हिटी आहे. त्यांनी जे काय आपण मोजमाप करतो दुर्बिणीच्या सहाय्याने, त्याचा अर्थ समजून घेण्यासाठी वैज्ञानिकांची आपल्याला गरज आहे. नुसते ऑब्झर्वेशन्स घेण्यासाठी, नुसती ती छायाचित्र टिपण्यासाठी नाही. आता इथे डावीकडे ग्रोथ इंडिया टेलिस्कोप दाखवतोय, हे पुन्हा दिवसा केलेलं टेस्टिंग आहे, की ती दुर्बीण आतमध्ये फिरतेय, वरती डोम हलतोय आणि हे सगळं त्याचं जे काम चालू आहे, ह्याचं जर पूर्ण काम कसं होतं बघितलं, तर खूप त्याच्यात क्लिष्ट अशी प्रोसिजर आहे, की हे अख्खं मी वाचणार नाहीये. पण एवढे त्याच्यात एकानंतर एक स्टेप्स आपल्याला करायला लागतात, की आकाशात काय चाललंय त्याचा अभ्यास करण्यासाठी. आणि हे सारखं करणं हा वैज्ञानिकांच्या वेळेचा सगळ्यात चांगला उपयोग नाहीये. मग ह्याच्यासाठी काय करावं? तर आमचा IITतला जो ग्रुप आहे, आम्ही स्टार लॅब स्पेस टेक्नॉलॉजी अँड ॲस्ट्रोफिजिक्स रिसर्च आणि इंडियन इन्स्टिट्यूट ऑफ ॲस्ट्रोफिजिक्स बँगलोर मधले आमचे सहकारी, आम्ही सगळ्यांनी मिळून ह्या टेलिस्कोपला पूर्णतः ऑटोमेट केलं. या दुर्बिणीचं सगळं काम पूर्णतः स्वयंचलित आहे. तर हे सगळे विद्यार्थी मागे आहे. तर ह्या सगळ्यांनी मिळून आणि ह्यांच्या आधीच्या आणि नंतरच्या विद्यार्थ्यांचंही त्याच्यावर काम चालू आहे. सगळ्यांनी मिळून केलंय असं, की ही दुर्बीण रात्री असा जर एखादा मेसेज आला, जर कुठून अनाउन्समेंट झाली, कुठला नवीन शोध लागलाय असं कळलं, तर ती दुर्बीण स्वतःहून त्या भागाकडे आकाशाच्या पॉइंट करते आणि छायाचित्र घेण्यास सुरुवात करते. 2018 मध्ये जे मी म्हणलं दुर्बीण कार्यरत झाली, हा आपल्या देशातला पहिला पूर्णतः रोबोटिक टेलिस्कोप आहे. आणि आपण रोबोटिक्स जेव्हा म्हणतो तेव्हा आपण कधी साय-फाय अशा गोष्टींमध्ये बघतो किंवा फॅक्टरीमध्ये रोबोट वापरलेले ऐकतो. तर ही दुर्बीण सुद्धा पूर्णतः रोबोटिक, पूर्णतः स्वयंचलित आहे. आता दुर्बिणीबद्दल झालं. दुसरं मी म्हणलो होतो ॲस्ट्रोसॅट. तर ॲस्ट्रोसॅट हा भारताचा स्पेस टेलिस्कोप आहे. एक उपग्रह आहे हा आणि त्याच्यात 5 वेगवेगळ्या प्रकारच्या दुर्बिणी आहेत, ज्या दृश्य प्रकाश म्हणजे ऑप्टिकल लाईटमध्ये एक काम करते. अल्ट्राव्हायोलेट किंवा यूव्ही किरण जे आपण म्हणतो, अतिनील किरण त्याच्यात काम करणारी एक दुर्बीण आहे आणि बाकीच्या 4 दुर्बिणी या एक्स-रे किरणांमध्ये आकाशाचा वेध घेतात. आणि ह्या सगळ्या दुर्बिणी आपल्याला जमिनीवरनं वापरता येत नाहीत, कारण आपली जे ॲटमॉस्फिअर आहे, पृथ्वीभोवतीची जी हवा आहे, त्याच्यात हे सगळे किरण अडतात. म्हणून आपल्याला जसं मागे ओझोन होल बद्दल आपण ऐकायचो खूप, की जेव्हा पोल्युशन वाढलं होतं, तेव्हा आकाशातला ओझोन कमी झाल्यामुळे यूव्ही किरण जमिनीपर्यंत पोहोचू शकत होते. आता नशिबाने लोकांनी छान त्याच्यावर कष्ट घेतल्यामुळे ओझोन होलचा प्रॉब्लेम कमी झालेला आहे. अजूनही पूर्ण गेलेला नाही. पोल्युशन अजूनही प्रॉब्लेम आहे. पण हे पोल्युशन बाजूला ठेवता आकाश आपलं जी हवा आहे, त्या हवेतनं एक्स-रे, क्ष-किरण आणि यूव्ही अतिनील किरण हे जमिनीपर्यंत पोहोचू शकत नाहीत. त्या किरणांचा वापर करून जर आपल्याला विश्वाचा अभ्यास करायचा असला, तर त्याच्यासाठी आपल्याला अंतराळात जायला लागतं. आणि ॲस्ट्रोसॅट हा त्याच्यासाठी पूर्णतः भारतीय उपक्रम आहे. आता त्याचं प्रक्षेपण बघूयात आपण आणि इथे काउंटडाऊन दिसतोय तुम्हाला 8, 7, 6. जेव्हा प्रक्षेपण सुरू होईल, तेव्हा त्या रॉकेटकडे थोडंसं लक्ष द्या आणि साधारण आत्ता एकदम सगळं तुम्हाला हादरे बसलेले ह्याच्यात दिसतायत. सगळं रॉकेट खूप हलतं. जेव्हा एखादा उपग्रह आपण प्रक्षेपित करतो, तेव्हा त्याच्यात प्रचंड धक्के बसतात पहिल्या लॉन्चच्या वेळेला. आणि तुम्हाला एक दुर्बीण बनवायची आहे, जी अतिशय म्हणजे ज्यातल्या अलाइनमेंट्स आपल्या केसाच्या 100व्या भागापेक्षा चांगल्या लागतात. ही ह्या सगळ्या लॉन्चमध्ये त्याला काहीही हानी होता कामा नाही. तर हे कसं बनवायचं? तर ह्याच्यासाठी तुम्हाला आता ॲस्ट्रोसॅटच्या ऐवजी मी पुढच्या एका उपग्रहाबद्दल सांगतो. दक्ष नावाचं एक नवीन प्रकल्प आता आम्ही ज्याच्यावर काम करतोय. दक्षमध्ये IIT बॉम्बे बरोबरच बाकी बऱ्याच देशातल्या संस्था TRL अहमदाबाद, TIFR मुंबई, RRI बंगलोर, अयुका, इस्रो ह्या सगळ्यांचा सहभाग आहे. आणि हे अजून एक प्रपोजल आहे, की आम्ही हे करू इच्छितो. असं आत्ता काम चालू आहे. तर दक्ष म्हणजे काय? तर साधारण अशा 2 दुर्बिणी बनवायच्यात, 2 उपग्रह बनवायचे, जे जगातल्या कुठल्याही इतर उपग्रहापेक्षा 10 पट चांगले असणार आहेत आणि हे पूर्णतः भारतात बनवलेले असतील. आणि असे 2 उपग्रह वापरून गॅमा रे बर्स्ट आणि लायगो बद्दलचे काही शोध घेण्यासाठी ह्याचा वापर करण्यात येणार आहे. तर आता दक्षचे उदाहरण का देतोय? कारण त्याचं आता आम्ही डिझाइन चालू आहे. त्याच्याबद्दल दक्षसाठी लागणाऱ्या सगळ्या गोष्टी आता बनवणं चालू आहे आणि त्या संदर्भात आपण आता बघूयात समजा, की दक्षचा प्रत्येक उपग्रह हा साधारण असा दिसणार आहे. त्याच्यात एक फ्रेम आहे आणि त्याच्यावरती अजून काही युनिट्स ज्याला आम्ही एमी बॉक्सेस म्हणतो त्या लावलेल्या आहेत. आता ही फ्रेम बघूयात, की ज्याच्यावरती हे सगळे डिटेक्टर्स लावले जाणार आहेत. ही जर मी एका रॉकेटवर लावून लॉन्च केली, तर त्याला हादरे बसून ही नीट भक्कम राहील का? हलेल. ह्याच्यासाठी आम्हाला अनेक कॅल्क्युलेशन्स आधी करायला लागतात. आणि त्या कॅल्क्युलेशन्समध्ये असं लक्षात येतं, की त्याच्यावर म्हणजे तुम्ही विचार करा, की एखाद्या लहान मुलाने त्याच्यावर चढून जर उड्या मारायला सुरुवात केली, तर जसं हलू शकेल, तसं वेगवेगळ्या प्रकारे हे हलेल आणि छोटं त्याच्यात काही जर हालचाल झाली तर लूज कॉन्टॅक्ट होऊन त्याच्यावरचे इलेक्ट्रॉनिक्स काम करणं बंद होणार आहेत का, किंवा असे सगळे काही त्याला अंतराळात जाऊन जर काही प्रॉब्लेम आला. आपण साधं जेव्हा फोनचा चार्जर लावतो तेव्हा तो असा केल्याशिवाय फोन कधी आपला नीट चार्ज होत नाही. आता विचार करा, अंतराळात हा उपग्रह पाठवला आणि जर त्याच्यात काही लूज झालेलं असलं तर तसं आपल्याला रिपेअर करता येणार नाही. म्हणून ही काळजी आम्हाला जो बनवतानाच घ्यायला लागते की ह्याच्यात काहीही प्रॉब्लेम व्हायचा नाही. इथे तुम्हाला जे दिसतंय ह्याला सिम्युलेशन असं म्हणतात, की आम्ही एका संगणकावर ह्याचे सगळं मॉडेल बनवलेलं असतं आणि रॉकेटमध्ये ज्या प्रकारचे हादरे बसतील तसे दिल्यावर ह्या स्ट्रक्चरचं काय होईल हे आम्ही तिथे कॅल्क्युलेट केलेलं असतं. पण नुसतं सिम्युलेशन नाही, हे लॅबमध्ये आम्ही खरं चेक करूनही बघतो. सो इथे उजवीकडे एक सिम्युलेशन दिसतंय आणि डावीकडे तुम्ही जर नीट बघितलं, इथे खाली एक तेलाचा थोडासा थर आहे जो हलताना दिसतोय आणि ह्या व्हिडिओमध्ये ही बॉक्स आम्ही बनवली आहे आणि ती एका व्हायब्रेशन टेबलवर लावून त्याला पूर्ण हादरे देऊन हलवलं जातंय, जेणेकरून आम्ही इथे आणि खाली एक बारीकसा सेन्सर तुम्हाला दाखवतो मी. एक क्षणात दिसेल. हा इथे एक सेन्सर लावलाय, ज्याने आम्ही मोजतोय की ते किती वागतंय आणि त्याच्यावरनं आम्ही ठरवणार की हे अंतराळात पाठवण्यासाठी योग्य क्षमतेचं आहे का, तेवढ्या क्वालिटीचं बंद आहे का. हादरे सहन करणं हा एक भाग झाला. अजून एक भाग म्हणजे आता समजा पृथ्वीभोवती हा उपग्रह आपण विचार करू की कक्षेत आहे पृथ्वीच्या. तो पृथ्वीभोवती फिरत असताना नुसतं अंतराळात व्हॅक्यूम आहे असा विचार करून पुरत नाही आपल्याला. कारण समजा डाव्या बाजूला सूर्य आहे असा विचार करा, तर डावीकडनं ऊन येतंय, उजवीकडे पृथ्वीची सावली पडली आहे. आता हा उपग्रह जेव्हा डाव्या बाजूला आहे तेव्हा त्याला सूर्याची पूर्ण ऊर्जा प्राप्त होतीये आणि तेव्हा त्याचं तापमान प्रचंड वाढतं. हे 60-70 डिग्री सेल्सिअस पर्यंत पोहोचू शकतं आणि तोच उपग्रह जेव्हा ह्या बाजूला येतो आणि पृथ्वीच्या सावलीत येतो तेव्हा तापमान प्रचंड कमी होतं आणि शून्यापेक्षा खाली 20-25 डिग्री पर्यंत जाऊ शकतं. आता ह्याची कक्षा ही साधारण 100 मिनिटाची असते. सो दर 45 ते 50 मिनिटात त्या उपग्रहावरचं तापमान हे 30 डिग्री पासून ते 70 डिग्री पर्यंत पोहोचतं. आपण घरी जेव्हा एखाद्या काचेचं भांडं घेऊनही त्याच्यात जर अचानक गरम काही होत ना तर काच तडकते. कुठलीही गोष्ट जेव्हा गरम होते तेव्हा प्रसरण पावते आणि हे जर खूप भरभर होत राहिलं तर त्यांनी ते तुटूही शकतं. त्यामुळे हा उपग्रह बनवताना ह्याचं डिझाईन करताना आम्हाला अशा तऱ्हेने डिझाईन करायला लागतं की तो अशा परिस्थितीमध्ये सुद्धा व्यवस्थित कार्यरत राहील आणि ह्याच्यासाठी पुन्हा हा जो भाग आहे डिझाईनचा हा पूर्णतः इंजिनिअरिंगचा भाग आहे आणि हे तंत्रज्ञान त्याच्यात जे लावतोय त्याच्यामुळे तो उपग्रह एकदा प्रक्षेपित झाला की आपली विज्ञानात पुढे प्रगती होणार आहे, कारण त्यांनी वापरून आम्ही खगोलशास्त्रीय अभ्यास करू शकणार आहोत. आता खगोलशास्त्रातलं तंत्रज्ञानाबद्दल आपण ऐकलं इतका वेळ. आता आपण तंत्रज्ञानातलं खगोलशास्त्र बघूया. सो विज्ञान तंत्रज्ञान आपण इतका वेळ बघत होतो की विज्ञानाचा अभ्यास करण्यासाठी तंत्रज्ञानाची गरज कशी आहे. आता त्याच विज्ञानामुळे तंत्रज्ञानात कुठे प्रगती झाली. खगोलशास्त्र म्हणजे आता ग्रहताऱ्यांचा अभ्यास झाला सगळं, ह्याच्यात तंत्रज्ञानाचा कसा काय कुठे संबंध येतो. सुरुवात करूया ॲस्ट्रोसॅट वरनच परत. ॲस्ट्रोसॅटचं मगाशी तुम्हाला मी नुसतं एक चित्र दाखवलं. हे ॲस्ट्रोसॅटचा ॲक्च्युअल फोटो आहे. इथे तुम्ही वरती हे जे दिसतंय हे कॅडमियम झिंक टेलराइड इमेजर म्हणून एक इन्स्ट्रुमेंट आहे. आता हे ॲस्ट्रोसॅट साधारण असं आहे, त्यातले हे वेगवेगळे जे दुर्बिणी आहेत. हा CZTI नावाचं हे इन्स्ट्रुमेंट आहे, ज्याच्यावर मी त्या टीमचा भाग होतो आणि त्याच्यात जे डिटेक्टर्स वापरले त्याच्यात मेन ते एक CZT किंवा CDZNTE म्हणतो आम्ही. कॅडमियम झिंक टेलराइड नावाच्या एका पदार्थाने बनलेले डिटेक्टर्स आहेत आणि हेच डिटेक्टर्स हॉस्पिटलमध्ये एक्स-रे काढायला वापरतात. त्यामुळे जे आपण ग्रहताऱ्यांच्या शोधासाठी वापरतोय त्यातलंच तंत्रज्ञान हॉस्पिटलमध्ये एक्स-रेलाही वापरलं जातं. तुम्ही हे डिटेक्टर्स काही ठराविक प्रकारच्या एक्स-रे युनिटमध्येच वापरले जातात. आपण सहसा हॉस्पिटलमध्ये गेलो तर तो मोठा एक्स-रेची फिल्म पूर्वी दिसायची. हल्ली त्याच्या काही हॉस्पिटल्समध्ये तुम्हाला फोटो फोनवर किंवा लॅपटॉपवर मिळतो आणि तेव्हा हे वापरण्यात आलेलं असतं. मी तुम्हाला इथे आणि ॲस्ट्रोसॅटचं एक मॉडेल दाखवलं, त्याचंच अजून एक उदाहरण देतो, की खगोलशास्त्रात तंत्रज्ञान कसं येतं. हे मॉडेल जे आहे इथे, हे दक्षचं 3D प्रिंटेड मॉडेल आहे. ॲस्ट्रोसॅटवर काम सुरू झालं होतं जवळ-जवळ 20-25 वर्षापूर्वी आणि तेव्हा हातात जर मला एखादी त्याची प्रतिकृती धरायची असली, तर ते बनवायला अवघड होतं. त्यामुळे जवळ-जवळ 15 एक वर्ष त्याच्यावर काम झाल्यावर शेवटी त्यांनी असे काही युनिट बनवून घेतले एका अ, बाहेरच्या कंपनीला कॉन्ट्रॅक्ट देऊन, भारतातल्याच एका कंपनीला कॉन्ट्रॅक्ट देऊन. पण त्याच्याऐवजी जेव्हा आम्ही दक्षबद्दल काम करत होतो, तेव्हा आम्ही इथे प्रयोगशाळेत बसून विचार करत असतो, की आपल्याला ह्या उपग्रहाच्या डिझाईनमध्ये कुठले भाग कसे असायला हवेत किंवा एखादा आकाशात इथे स्रोत असला तर त्यांनी ह्या आपल्याला कुठल्या डिटेक्टर्सवर काय दिसू शकेल. त्या हातात मॉडेल असणं हे अतिशय गरजेचं असतं. गेल्या 25 वर्षात तंत्रज्ञान इतकं पुढे गेलंय, की हे आम्ही सहज एका दिवसात 3D प्रिंट करून घेऊ शकलो आणि हे आम्हाला जेव्हा विद्यार्थ्यांबरोबर किंवा इतर शास्त्रज्ञांबरोबर आम्ही चर्चा करत असतो, तेव्हा हे हातात असणं खूप उपयोगी ठरतं. आपण तंत्रज्ञानाकडे हॉस्पिटलमध्ये वापरणारे एक्स-रे डिटेक्टर्स वगैरे बघायच्या या व्यक्तींकडे जाऊ. हा फोटो तुम्ही कदाचित ओळखणार नाही, पण अल्बर्ट आइन्स्टाईन हे कायमच असे केस आणि रॅक करून उभे असलेले नसायचे. हा अल्बर्ट आइन्स्टाईनचा फोटो आहे आणि त्यांचे 2 अतिशय फेमस थिअरी आहेत त्यांच्या. 2 महत्त्वाचे सिद्धांत आहेत. त्यांनी खूप वेगवेगळ्या विषयात त्यांचंही काम होतं. पण स्पेशल थिअरी ऑफ रिलेटिव्हिटी आणि जनरल थिअरी ऑफ रिलेटिव्हिटी हे सापेक्षतावादाचे 2 सिद्धांत अल्बर्ट आइन्स्टाईन यांनी जे मांडले. तर आधी हे रिलेटिव्हिटी सापेक्षता म्हणजे काय ह्याच्याबद्दल थोडंसं बोलू आणि मग त्याचा तुम्हाला आम्हाला रोजच्या आयुष्यात काय फरक पडतो ह्याच्याकडे वळूयात आपण. आता आइन्स्टाईन यांनी काय सांगितलं, की अवकाश म्हणजे आपल्या आजूबाजूचं सगळं काही आणि काळ, वेळ ह्या 2 गोष्टी आपण वेगळ्या-वेगळ्या विचार करतो, की साधारण आता माझं ऑफिस आज होतं तसंच उद्या असेल. थोडा पसारा जास्ती असेल त्या पलीकडे काही बदलणार नाही आणि वेळ पुढे-मागे गेल्यावर फार त्याच्यात फरक पडत नाही आपल्याला दैनंदिन आयुष्यात. पण त्यांनी असा शोध लावला, की अवकाश आणि काळ हे दोन्ही एकत्र असतं आणि सगळं मिळून स्पेस टाईम असा हा प्रकार आहे, की तुम्ही स्पेसबद्दल, अवकाशाबद्दल, आपल्या आजूबाजूच्या सगळ्या गोष्टींबद्दल काळाशिवाय विचार करू शकत नाही. आणि त्याचा तुम्ही अशा प्रकारचं एक उदाहरण कदाचित बघितलं असेल, की एखादी जड वस्तू जर असली, तर त्याच्या भोवतीचा अवकाश काळ हे जास्ती वाकतं किंवा कर्व्हेचर, बेंडिंग ऑफ स्पेस टाईम ज्याला म्हणतात. पण ह्याच्यात गंमत अशी होते, की आपण असं जे चित्र बघतो एखादं, तेव्हाही की पृथ्वी त्याच्यात ठेवली आहे ह्या स्पेस टाईममध्ये आणि त्याच्यामुळे ते खाली गेलंय. खाली ह्याचाच अर्थ आइन्स्टाईन बदलला, की गुरुत्वाकर्षणाची दिशा ह्याला आपण सहसा खाली म्हणतो. त्यामुळे हे चित्र बघण्यापेक्षा हे जास्ती योग्य आहे इथे, की समजा तुम्ही असा विचार करा, की कुठेतरी मी ही ही जी ग्रिड काढली आहे इथे, म्हणजे आता एखाद्या बिल्डिंगभोवती रंग देताना जसं बांबूची एक चौकट बांधलेली असते ना, तशी समजा अंतराळात सगळीकडे आहे आणि अचानक त्याच्यात मध्ये कुठेतरी एखादी घन गोष्ट आपण ठेवली, एखादी वजनदार गोष्ट आपण जर मध्ये ठेवली, तर त्याच्या भोवतीच्या सरळ रेषा सरळ राहणार नाहीत, वाकतील. आणि ह्या वाकलेल्या अवकाश काळात जेव्हा एखादी गोष्ट सरळ जायचा प्रयत्न करते, तेव्हा ती गोल जात राहते. आता आजचं आपलं हे व्याख्यान हे रिलेटिव्हिटी किंवा व्यापक सापेक्षतावादाबद्दल नाहीये, त्यामुळे ह्याहून जास्ती मी खोलात इथे जाणार नाही. पण आइन्स्टाईन यांचा हा सिद्धांत आपण E=mc² सहसा ऐकलेलं असतं. पण जनरल थिअरी ऑफ रिलेटिव्हिटी ही खरं गुरुत्वाकर्षणाची थिअरी आहे. गुरुत्वाकर्षणाबद्दलचा सिद्धांत आहे. आता ह्यानी आपल्याला काय फरक पडणार आहे पण? तर असा विचार करू आपण आधी एक स्पेशल थिअरी, विशेष सापेक्षताबद्दल आपण बघू, की समजा आइन्स्टाईन आहेत इथे आणि त्यांच्यासमोर एक घड्याळ आहे. हे जर स्टॉपवॉच आपण विचार करू आणि हे जर सुरू केलं, तर दर सेकंदाला आपल्याला 1 सेकंद होताना दिसेल. म्हणून तर आपण त्याला सेकंद म्हणतो. पण त्यांनी असं शोध लावला आणि इतर सहकाऱ्यांबरोबर त्यांनी हे सिद्ध केलं, की हे घड्याळ जर हलत असलं, तर आपण परत ह्याला 0 करू आणि आता हे घड्याळ उजवीकडे हलायला लागेल, तर घड्याळ स्लो होतं. घड्याळाचे जे आपल्याला सेकंद बदलताना दिसतात, ते अजून हळू होत जातात. इथे अर्थात मी अतिशयोक्ती केली आहे. एवढ्या हळू हलणाऱ्या घड्याळांनी एवढा फरक पडणार नाही. पण 1 सेकंद बदलताना दिसायला 1 सेकंदापेक्षा जास्त वेळ लागतो. आणि हा जो परिणाम आहे, हा प्रयोगशाळेत आणि खूप ठिकाणी दिसून आलेला आहे. अगदी विमानातनं सुद्धा जेव्हा अतिशय चांगल्या प्रकारची घड्याळं वापरून जेव्हा लोकांनी ह्याचं मोजणी केली तेव्हा त्यांचा जो काय प्रेडिक्शन होतं त्यांचं ते खरं आहे असं दिसून आलं. ही झाली स्पेशल थिअरी ऑफ रिलेटिव्हिटी. आणि व्यापक सापेक्षतेचा जो त्यांचा सिद्धांत आहे त्याच्यात त्यांनी अजून एक सांगितलं की कुठल्याही घन गोष्टीच्या जवळ आपण आलो तर वेळ हळू जाते. इथे आता पुन्हा पृथ्वी आहे आणि आपण 2 घड्याळ एकत्र सुरू करणार आहोत. एक पृथ्वीच्या जवळ आहे, एक पृथ्वीच्या लांब आहे. आइन्स्टाईनच्या सिद्धांताप्रमाणे हे घड्याळ जे पृथ्वीच्या जवळ आहे ते थोडं हळू चालेल आणि हे घड्याळ त्यापेक्षा थोडं जोरात चालेल. योग्य खरी वेळ दाखवणारं घड्याळ हे कुठल्याही वजनाच्या गोष्टीपासून अतिशय अतिशय लांब अंतरावर असलं पाहिजे तरच योग्य वेळ दाखवेल. आता ही दोन्ही घड्याळ आपण सुरू करूया. हे परत दाखवतो की पहिलं सेकंद बदलताना दोन्हीत फरक पडला असं नाहीये. खालचं घड्याळ कायमच अजून हळू चालतंय, त्यामुळे जसा वेळ पुढे जातोय तसा त्यातला फरक वाढत चाललाय. ठीक आहे, अचानक आपण खगोलशास्त्रातनं घड्याळ आणि वेळा आणि आइन्स्टाईन यांच्या सिद्धांतांपर्यंत का पोहोचलो? हे बघा, ह्या गोष्टींपैकी तुम्ही गेल्या वर्षभरात काही वापरलंय? निश्चितच. तुम्ही घरी गोष्टी ऑर्डर केल्या असतील, कधी कंटाळा आला घरी बसून पिझ्झा मागवला असेल. ह्या सगळ्यात आपण काय करतो? फोनवर लोकेशन सांगतो आणि फोनवर लोकेशन सांगण्यासाठी 2 तंत्रज्ञान वापरले जातात. त्याच्यात एक अतिशय महत्त्वाचं म्हणजे जीपीएस, ग्लोबल पोझिशनिंग सिस्टम. असाच आता भारताचा इंडियन रिजनल नॅव्हिगेशन सॅटेलाइट सिस्टम IRNSS म्हणूनही प्रकल्प आहे. पण मी आत्ताच्या उदाहरणासाठी जीपीएस वापरतो. तर जीपीएसचे जे उपग्रह आहेत ते कसं, जीपीएस सिस्टीम कशी चालते, तर हे वेगवेगळे उपग्रह वेगवेगळ्या कक्षेत आहेत पृथ्वीच्या भोवती आणि त्यातनं साधारण अगदी सोप्या शब्दात सांगायचं तर बीप 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 असा एक सिग्नल येत राहतो आणि हा संकेत किमान 4 उपग्रहांमधनं घेऊन त्यांच्या वेळातला फरक जाणून पृथ्वीवर आपण कुठे आहोत हे तुमचा फोन त्यातनं निष्कर्ष काढतो. आता हा उपग्रह हा पृथ्वीच्या पासून जमिनीपासून 20,000 किलोमीटर उंचीवर, पृथ्वीच्या सेंटर पासून 26,000 किलोमीटरवर आहे. त्यामुळे आइन्स्टाईनच्या सिद्धांताप्रमाणे तिथे वेळ आपल्यापेक्षा ही थोडी जोरात चालली आहे. आणि एवढंच नाही तर तो उपग्रह पृथ्वीभोवती साधारण सेकंदाला 5.5 किलोमीटर या वेगाने हलतोय. ह्याचा अर्थ असा की त्याच्यात जो स्पेशल थिअरी ऑफ रिलेटिव्हिटीमुळे पण फरक पडेल आणि त्यातलं घड्याळ आपल्याला हळू जाताना दिसेल. तो एका पहिल्या कारणामुळे जोरात जाताना दिसेल, दुसऱ्यामुळे हळू. तर हे सगळं मग किती फरक पडतो ह्यानी? तर समजा आपण सापेक्षतेचे प्रमाण नीट सोडवले नाहीत, तर ही समीकरणं नीट जर नाही वापरली तर एका दिवसात साधारण 38 मायक्रोसेकंद इतका फरक पडेल. म्हणजे सेकंदाचा 1000वा भाग, जसं मीटरचा 1000वा भाग मिलीमीटर, तसं सेकंदाचा 1000वा भाग मिलीसेकंद आणि त्याचा 1000वा भाग म्हणजे मायक्रोसेकंद. 38 मायक्रोसेकंद. म्हणाल काय आता आपण भारतात राहतो, 38 मायक्रोसेकंद आपल्याला 38 मिनिटं उशीर झाला तरी उशीर म्हणत नाही. पण हे तुमची माझी गोष्ट नाहीये ना. आपण बोलतोय तो सिग्नल, जो संकेत येतो तो रेडिओ लहरींद्वारे येतो. त्या जातात प्रकाशाच्या वेगाने. प्रकाशाचा वेग आहे सेकंदाला 3 लाख किलोमीटर. म्हणजे ही जर 38 मायक्रोसेकंद एका दिवसातली फक्त जो वेळेतला फरक पडेल हा घेतला तर 11 किलोमीटर साधारण फरक पडतो. म्हणजे तुम्ही जर आज आयुकात जायचं असतं तुम्हाला हे व्याख्यान ऐकायला आणि तुम्ही टॅक्सीत बसलात आणि आयुकाचं लोकेशन लावलं तर चुकून कर्वेनगरला पोहोचला असता. एवढा फरक पडू शकतो. आता ह्याची गंमत बघा ना, आइन्स्टाईन साधारण 1905 ते 1915 या काळात ह्या सगळ्या गोष्टींवर काम करत होते. ते तेव्हा बसून विचार करत होते की विश्वाचं मूळ स्वरूप काय, गुरुत्वाकर्षण, गुरुत्वीय बळ कशामुळे निर्माण होतं. आणि त्यांनी हा जो मूलभूत संशोधन त्यांनी हे जे केलं त्याच्यामुळे आज आपण घरी बसून आळशीपणे पिझ्झा मागवू शकतो. आणि हे फार महत्वाचं आहे इथे की मूलभूत संशोधन जेव्हा आपण करतो तेव्हा त्याचा पुढे काय उपयोग होईल. आइन्स्टाईनला तेव्हा हे नक्की वाटलं नव्हतं की आपण घरी बसून त्याच्यावर मग गोष्टी ऑर्डर करत असू एक दिवस. तेव्हा संगणक नव्हते, काही नव्हतं, अशा काळातली ही गोष्ट आहे. पण त्याचे आज कुठे उपयोग होतात, आज काय फायदे होऊ शकतात हे तेव्हा सांगणं अशक्य असतं आणि म्हणून मूलभूत संशोधन ही अतिशय महत्वाचं आहे. आइन्स्टाईन यांच्या कुठलीही गोष्ट आली की त्याच्यात ऑफकोर्स आपण कृष्णविवरांबद्दल बोललोच पाहिजे. तर त्यांनी त्याचबरोबर अजूनही एक भाकीत केलं होतं ग्रॅव्हिटेशनल वेव्हज किंवा गुरुत्वीय लहरींबद्दल. तर इथे एक आता तुम्ही बघताय हे खरं चित्र नाही, हे सिम्युलेटिंग एक्स्ट्रीम स्पेस टाइम्स या ग्रुपनी केलेलं कॅल्क्युलेशन आहे, त्यावरनं हे चित्र बनवण्यात आलेलं एका संगणकावर. पण तुम्ही बघताय 2 कृष्णविवर आहेत इथे, जी एकमेकांभोवती फिरतायत आणि एकमेकांभोवती फिरल्यामुळे त्यातनं ऊर्जा उत्सर्जित होतीये. ग्रॅव्हिटेशनल वेव्ह, गुरुत्वीय लहरींच्या माध्यमातून, आणि त्यामुळे त्यांची ऊर्जा एकूण कमी होत ते शेवटी जवळ-जवळ जाऊन एकत्र टक्कर झाली, त्यांचं विलिनीकरण झालं. आणि ह्या सगळ्यातनं ज्या गुरुत्वीय लहरी निर्माण होत आहेत, त्या 2015 सालापासून आपल्याला दिसतायत लायगो या प्रकल्पाद्वारे. इथे लायगो म्हणजे 2-4 किलोमीटर लांबीचे मोठे आर्म्स असतात आणि त्याच्यात इंटरफेरोमेट्रीच्या सहाय्याने गुरुत्वीय लहरींचा शोध घेण्यात येतो. आयुकाची आज बाकी जर व्याख्यानं तुम्ही ऐकली असतील तर त्याच्यात याबद्दल अजून ऐकलंच असेल. हे आता 2 उपक्रम लायगोचे हे अमेरिकेत आहेत. एक काग्रा म्हणून जपानमध्ये आहे आणि एक इटलीत व्हर्गो म्हणून आहे. पण ह्यातला पुढचा प्रकल्प हा भारतात आपण घेणार आहोत आणि आपल्या महाराष्ट्रातच औंधा नागनाथ म्हणून नांदेडजवळ एक गाव आहे. त्याच्याजवळ लायगोची ही जमीन आहे आणि भारतात लायगो उपक्रम हा जगातला लायगोचा हा 3रा फक्त हे असणार आहे आणि एकूण जगात 5वा प्रकल्प ज्याच्यात ह्या गुरुत्वीय लहरींचा शोध घेणं शक्य होईल. गुरुत्वीय लहरींचा शोध हा अतिशय क्लिष्ट असा उपक्रम आहे. आइन्स्टाईन यांचं स्वतःचं म्हणणं होतं की या कधीच दिसणं शक्य नाही, कधीच यांचं मोजमाप होणं शक्य नाही, कारण हा अतिशय सूक्ष्म असा परिणाम असतो त्याचा. जेव्हा लायगो मधनं एखादी गुरुत्वीय लहर जाते तेव्हा त्यातला प्रत्येक त्याच्यात आरसे वापरून त्याच्यातलं अंतर मोजलं जातं आणि तो आरसा हा एका अणूच्या 1000 पट कमी हलतो. एवढं बारीक त्यातलं हलणं आपल्याला त्याच्यात मोजायचं असतं. हे अतिशय अवघड असं काम आहे आणि त्याच्यासाठी खूप वेगवेगळ्या विषयातली एक्सपर्टीज लागते आणि खूप वेगवेगळ्या विषयांचा अभ्यास, खूप वेगवेगळ्या विषयांचे तज्ञ एकत्र काम करूनच हे होऊ शकतं. इथे ही स्लाइड मी अख्खी मराठीत केली नाही, कारण खरं तर ह्याची मराठी नावं मला आणि कदाचित तुम्हालाही पूर्ण माहिती नसतात. तर लेझर्स, व्हॅक्यूम्स, ऑप्टिकल इंजिनिअरिंग, सेन्सर्स ह्या सगळ्या प्रकार उजवीकडे इंजिनिअरिंग बाजूचे आले. खगोलशास्त्रातले आणि संगणकातले गोष्टी इथे आल्या की कम्प्युटेशन आलं वेगवेगळं, हाय परफॉर्मन्स कम्प्युटिंग. इथे वेगवेगळ्या प्रकारच्या दुर्बिणी आल्या, ज्याच्यात आपण ॲस्ट्रोसॅट बद्दल ऐकलं किंवा GMRT नारायणगावला जी रेडिओ दुर्बीण आहे ती आली. फिजिक्सचे वेगवेगळे प्रकार आले. हे सगळं एकत्र येऊन हा जगातला सगळ्यात सेन्सिटिव्ह एक प्रकल्प होणार आहे आणि त्याच्यात अनेक नवीन तंत्रज्ञानं त्याच्यात विकसित होत आहेत. उदाहरणार्थ भारतासाठी जर म्हणलं तर जगातली सर्वोत्कृष्ट लेझर ही लायगोमध्ये वापरली जाते आणि लेझर तर तुम्हाला माहिती आहे की ह्याचे फायदे असतातच भरपूर लेझर्सचे. जसं अगदी आपण डोळ्याची लेसिक सर्जरी करून घेतो तिथपासून ते आपण वर्गात शिकवताना एखाद्याने लेझर पॉइंटर वापरला, जेव्हा लेझरची स्टॅबिलिटी आणि क्वालिटी सुधारते तेव्हा त्याचे परिणाम ह्या सगळ्या विषयांमध्ये पडतात. व्हॅक्यूम सिस्टीम ते जे मोठे पाईप होते ते पूर्णतः निर्वात असतात. त्याच्यात एखादा धुळीचा कण किंवा धुळीचा कण सोडा, हवेचा एखादा मॉलिक्यूल जरी मध्ये आला तरी त्यांनी हे सगळं मेजरमेंट जे घ्यायचे असतात ते चालेनासे होतात. त्यामुळे सगळ्यात मोठ्या प्रमाणात व्हॅक्यूम बनवण्यासाठीचं तंत्रज्ञान लायगोसाठी विकसित करण्यात आलं आहे आणि त्याचेही फायदे जिथे जिथे आपल्याला व्हॅक्यूम तंत्रज्ञान लागतं, निर्वात क्षेत्र बनवायला लागतात, तिथे सगळीकडे होतात. मी म्हणलं की त्याच्यात आरसे वापरले जातात ज्यांची हालचाल आपल्याला एका अणूच्याही 1000व्या भागा एवढी कमी होते आणि ती मोजायला लागते. आता एक उदाहरण जर द्यायचं तर इतक्या आपल्या आजूबाजूला गोष्टी हलत असतात. तुम्ही जर एखाद्या रेल्वेच्या जवळ राहत असलात तर शेजारनं ट्रेन गेल्यावर आपल्याला हादरे जाणवतात. आपल्याला गणपतीत ढोल ताशे पथक असतात तेव्हा आपल्या घरची टेबलं हलताना जाणवतात. ह्या सगळ्यापासनं सुद्धा आपल्याला ह्यातनं अलगाव करून ते आरसे जे आहेत ते एवढे शांत एका ठिकाणी ठेवायचे, त्याच्यासाठी प्रचंड सेस्मिक आयसोलेशन म्हणजे भूकंपापासून अलगाव करण्यासाठी प्रणाली जी विकसित करण्यात आली आहे ती सर्वोत्कृष्ट प्रणाली आहे आणि त्यातनं पुन्हा पुढे आज त्याचा उपयोग आहे लायगोसाठी. 10 वर्षात 20 वर्षात कदाचित आपल्याला अर्थक्वेक प्रूफ भूकंप रहित बिल्डिंग्स त्यातनं बनवता येतील, माहित नाही. आज हे विज्ञान आहे, त्यातनं पुढे तंत्रज्ञान काय निर्माण होईल हे आज सांगणं शक्य नाही. तसंच उच्च कार्यक्षमता संगणक, हाय परफॉर्मन्स कम्प्युटिंग ज्याला म्हणतात, की सुपर कम्प्युटर्स वेगवेगळ्या प्रकारचे आणि त्यातनं जास्तीत जास्ती त्या एका संगणकातनं जास्तीत जास्ती फायदा मिळवणं, जास्तीत जास्ती प्रश्नांची उत्तरं शोधून काढणं, हा ह्याच्यावर खूप संशोधन चालू आहे लायगोसाठी. कारण ह्याच्यासाठीचे जे कॅल्क्युलेशन करायला लागतात, जे संगणन करायला लागतं, ते अतिशय क्लिष्ट आहे आणि जगातले सगळे सुपर कम्प्युटर एकत्र लावून तर आपण फक्त एका प्रकल्पाला देऊ शकत नाही. त्यामुळे त्याच्यातही भरपूर रिसर्च चालू आहे. तर इथे विज्ञान आणि तंत्रज्ञान ह्या ज्या दोन गोष्टी आहेत, त्या कायम एकत्र कार्यरत असतात. आजचं जे विज्ञान आहे त्यातनं उद्या नवीन तंत्रज्ञान विकसित होईल आणि तेच तंत्रज्ञान पुढे जाऊन अजून विज्ञानात नवीन शोध लावण्यालाही त्याचा आपल्याला उपयोग होईल. आणि तुमच्यापैकी काही जण कदाचित शास्त्रज्ञ बनतील लवकरच आणि ह्याच्यात आमच्याबरोबर कामाला येतील. याबरोबर ह्या टप्प्यावर आपण आज थांबूया आणि आता प्रश्नोत्तरांकडे वळूया. धन्यवाद. आता प्रश्नोत्तर घेऊ शकतो. तुम्हाला जर या विषयाबद्दल किंवा आज ऐकलेल्या इतर कुठल्याही व्याख्यानांमधनं तुम्हाला जर काही प्रश्न असले तर तुम्ही ते YouTubeच्या चॅटमध्ये विचारू शकता आणि आम्ही इथे त्याची उत्तरं देऊ. आज विज्ञान दिवसाच्या निमित्ताने बरीच ऑनलाईन लेक्चर्स आहेत आणि वेगवेगळ्या ठिकाणी वेगवेगळे विषय आज तुम्हाला ऐकायला मिळतील. तर आपण इथे बाकी प्रश्न येस तोपर्यंत त्याच्याबद्दलही काही सांगू शकतो मी, की तुमच्या शहरात तुमच्या आसपास ज्या कुठल्या वैज्ञानिक संस्था आहेत त्या संस्थांमधनं तुम्ही त्यांचे जर वेबसाईट्स बघितल्या तर त्यांनी आज काय प्रोग्राम केलेले आहेत ऑर्गनाइज, त्याच्याबद्दल तुम्हाला माहिती मिळेल. त्यातले बरेचसे ऑनलाईन आहेत. काही ठिकाणी तिथे जाऊन तुम्ही बघू शकता आणि त्याचा तुम्ही निश्चित फायदा घ्यावा असं मी तुम्हाला सांगेन आवर्जून अगदी. लायगोच्या संदर्भात विचारला जाणारा एक बऱ्याचदा विचारला जाणारा हा प्रश्न आहे, की भारतात लायगो प्रकल्प जेव्हा आपण करतोय तेव्हा त्याच्यात महाराष्ट्रात हा प्रकल्प येतोय, त्याच्याने महाराष्ट्रासाठी काय फायदे आहेत, त्याने भारतासाठी काय फायदे आहेत, याबद्दलच्याही काही गोष्टी मी मगाशी म्हणलोच स्लाइड्स बरोबर. तर त्यापुढे अजूनही काही गोष्टी आपल्याला म्हणता येतील, की ज्या संस्था ह्याच्यावर आता काम करतायत, जसं RR-CAT मध्ये काम चालू आहे, IPR मध्ये काम चालू आहे. RR-CAT मध्ये लेझर तंत्रज्ञानावर त्यांनी जेव्हा प्रयोग सुरू केले आणि विकसित अजून करायला सुरुवात केली, तेव्हा लायगोसाठी जे ध्येय त्यांनी स्वतःसाठी ठेवलंय, त्यामुळे तंत्रज्ञान आता खूप जोरात खूप पुढे विकसित त्यांचं व्हायला लागलंय आणि लायगो ह्या उपक्रमामुळे त्यांना जगातल्या इतर लेझर एक्सपर्ट्स बरोबर काम करायला मिळालं आणि त्यांनी आपल्याकडचं लेझर तंत्रज्ञान खूप झपाट्याने पुढे गेलं. अशाच प्रकारे इतर गोष्टींमध्ये सुद्धा जसं अगदी लायगोशी निगडीत असलेले जे इतर विषय आहेत, खगोलशास्त्रासाठी नवीन दुर्बिणी बनवण्यासाठी एक उपक्रम आम्ही हाती घेतोय, की लायगोच्या साईटवर महाराष्ट्रातच आपल्याला तिथे कदाचित काही दुर्बिणी लावता येतील, जेणेकरून लायगो ज्या वस्तूंचा अभ्यास करताय त्याच स्रोतांचा अभ्यास आपल्याला ऑप्टिकल दृश्य प्रकाशातही करता येईल. तर तुमच्या प्रतिक्रिया आणि प्रश्न मला वाटतं आता लोक अजूनही विचार करतायत, त्यामुळे आपण आजचा हा सेशन इथे थांबवूयात आणि तुम्हाला लायगो इंडियाचे जे सोशल मीडिया चॅनल आहेत, फेसबुकवर, युट्यूबवर, ट्विटरवर, इथे कुठेही तुम्ही आम्हाला नंतर जरी प्रश्न पाठवले तरी आम्ही त्याचे लवकरात लवकर उत्तर द्यायचा पूर्ण प्रयत्न करू. धन्यवाद.
Thank you very much, Varun, for this very interesting talk. We are nearing the end of today's celebration of National Science Day. The last session is a fun one called Science Made Simple. So here students explain how statistical mechanics, which is widely applied in astrophysics, can also be applied to diverse fields like economics and biology. Let's watch these clips.
Statistical mechanics is a probabilistic approach to equilibrium macroscopic properties of large number of degrees of freedom. In short, we use principles and procedures of statistics and apply them to laws of classical and quantum mechanics. Applying statistical mechanics on a gas enclosed in a box gives us cars, trains, airplanes. Applying it on quantum entities gives us superconductivity, Bose-Einstein condensate, and even explains white dwarfs and neutron stars. But probability and statistics needs no context. So could it be applied to a very different field like economics? The answer is yes. To give an analogy, in statistical physics, identical molecules in a gas spontaneously develop an unequal distribution of energies by random collisions with other molecules. Analogously, an unequal probability distribution can spontaneously develop in an economic system by random interaction between economic agents. So, let us begin. Let's briefly review the basics of statistical physics, starting from a discrete model of a quantum paramagnet. Consider n atoms and label the individual atoms with integer index j, goes as 1, 2, 3 till n. Each atom has an internal quantum degree of freedom called spin and can be in one of the q discrete states. Their states are labeled by the index k, goes as 1, 2, 3 till n. The system is placed in an external magnetic field, so each discrete state has a different energy upsilon k. Nk denotes the number of atoms in state k, so the summation over k of nk is equal to n, the total number of atoms. The number of microstate for this system turns out to be this. By using formula for entropy and Stirling approximation, we get this expression for entropy. The typical constraint for a closed system are that the total number of atoms n and the total energy E are fixed. By using Lagrange multipliers alpha and beta, the maximization of entropy is achieved by setting the derivatives of S tilde with respect to nk to 0. We find that the occupation numbers for states k depend exponentially on energies of these states. Here the parameter t equals 1 by beta and mu equals alpha times t. This is the fundamental law of equilibrium statistical physics known as the Boltzmann distribution. However, one can see that the above derivation is just an exercise in the theory of probabilities and is not specific to physics. Thus, it can be applied to statistical ensemble of different nature. Economy is also a big statistical system consisted of a large number of economic agents. Thus, it is tempting to apply the above formalism to economy as well. Consider an ensemble of n economic agents and characterize their states by the amount of money they hold. Let's denote the money balance of the agent J by Mj. Ordinarily, economic agents can only receive money and give money to other agents and are not permitted to manufacture money. Let's consider an economic transaction between agents I and J, when agent I pays money delta M to agent J for some goods and services. The money balance of the agent changes as Mi goes to Mi minus delta M and Mj goes to Mj plus delta M. However, the total amount of money of the two agents before and after the transaction remains the same. This is the local conservation of money. We can see that the transfer of money is analogous to transfer of energy in molecular collisions. Also, unlike ordinary economic agents, a central bank or a central government can inject money into the economy, thus changing the total amount of money in the system. This process is analogous to influx of energy into the system from external sources. We consider a model where the central authority do not inject additional money, so the total amount of money in the system is fixed. This gives us the global conservation law for money. A potential problem with conservation of money is about a debt. Let's assume that agents are not allowed to have debts. That is, money balance of agents cannot drop below zero, and a transaction takes place only when an agent has enough money to pay the price. If nk represents the number of agents whose money balance is between a reasonably small money window and putting the constraints of global conservation of money and maximizing the entropy, gives us again the Boltzmann distribution, where Tm is the money temperature given by Tm equals m by n. Researchers performed computer simulations of money transfer between agents. Initially, all agents were given the same amount of money. Then a pair of agents was selected at random and the amount delta m was transferred from one agent to another. And this process was repeated many times. After a transitionary period, money distribution converged to a stationary form, and the distribution was well fitted by an exponential function. Therefore, computer simulation shows how the entropy of money distribution grows from an initial value, when all agents have same money, to a maximum value at statistical equilibrium. From the standpoint of an individual economic agent, debt may be considered as negative money. In this case, it is the algebraic sum of the positive cash M and negative debt D, where MB is the original amount of money in the system. So the consequence of debt is not a violation of conservation law, but a modification in the boundary condition by permitting negative balances. So M can take negative values. When computer simulations were repeated on debts of the agents, the probability distribution of money doesn't stabilize. Well, common sense as well as financial crisis indicates that an economic system cannot be stable if unlimited debt is permitted. We can see this from our Boltzmann model, where C equals 1 by Z, and Z is given by this expression. When the debt is permitted and is not limited by any constraint, the sum over both positive and negative values of Mk diverges. Thus, we modify the boundary condition in order to prevent unlimited growth of debt by allowing the agents to go into debt up to a finite value, Md. In this model, the probability again has the exponential shape, but with new boundary condition that maximum debt of each agent is limited to Md. And it's found that the Boltzmann law fits the computer simulations quite well. The conclusion is simple. Statistical approach and entropy maximization are very general methods for studying big ensembles, be it physical or economical. The question is about how we apply them.
Hello. In this video, I will briefly talk about one of the applications of statistical mechanics in biology, which is studying the ligand-receptor binding and its dependence on the concentration of ligands. Ligands are small molecules or ions that get attached reversibly to certain proteins which are known as receptors. These two occur in closely matched pairs. When the ligand gets attached to the receptor, the shape of the receptor changes, which might trigger some kind of a response. Many kinds of ligands act like messengers within or across cells. Some other kinds of ligands switch particular enzymes on for a short duration of time and make them functional. Some other kinds act like keys to certain channels across membranes. For example, in this case, when this ligand comes and gets attached to this receptor, the channel opens, allowing the passage of certain molecules and ions across the membrane. Another example of receptor-ligand pair is hemoglobin and oxygen molecules. The diffusion of oxygen molecules is not an efficient process. Therefore, these oxygen molecules get bound to hemoglobin and get transported efficiently within the body. I'll talk more about hemoglobin later in this video. The ligands move randomly through the fluids of an organism, and this is where statistical mechanics comes in. When the concentration of the ligands is large enough, some of them will eventually encounter a receptor and get bound to this. So let's quantify this process. Imagine an isolated system that is represented by a box of solution containing a single receptor and L ligands. So let us divide this box into omega number of sub-boxes. The size of these boxes is such that only a single ligand can occupy a box at given time. The size of this box doesn't matter as long as the number of boxes, omega, is much more larger than the number of ligands, which is L. Different microstates of this system correspond to the position of different ligands in different boxes. This system is very close to that of an ideal gas, wherein here any two ligands do not interact with each other since the solution is very dilute. This particular system has only two microstates, one in which a ligand is attached to the receptor and another in which no ligand is attached to the receptor. We can find the same treatment as the one used for canonical ensemble to find the weights associated with these two microstates. Here, W0 is the weight associated with the microstate and no ligand is bound to the receptor, whereas W1 corresponds to the one where a single ligand is attached to the receptor. Here, E solution is the energy of a ligand when it is not attached to the receptor, whereas E bound is its energy when it is bound to the receptor. Knowing these two weights, we can calculate the probability of a ligand getting bound to the receptor, and it can be written in terms of the concentration of the ligands C. So as you can see, this probability depends only on the concentration of the ligands and the energy difference between the two states of the ligand, one where it is bound to the receptor and the other when it is not bound to the receptor. This function is known as the Hill function and can be used to model actual systems. This plot shows the data of oxygen binding to myoglobin as a function of partial pressure or concentration of oxygen. As you can see, the Hill model provides an excellent fit to the data. Now let us look at a slight modification of this system, cooperative binding, which is seen in hemoglobin. As mentioned earlier, hemoglobin molecule has four sites at which oxygen molecules can get attached. Here, the total binding energy is not simply the addition of all the binding energies. That is, the binding energy of the first ligand that get attached is not equal to that of the second ligand that gets attached, which is completely different from the third and the fourth attached ligand. Thus, cooperative binding can be explained by taking into account the interaction energy between these bound ligands. Let us describe the state of hemoglobin molecule by a set of four numbers sigma 1, sigma 2, sigma 3, sigma 4, where the numbers correspond to each site where an oxygen can get bound. Sigmas take value 1 when that particular site is occupied by an oxygen molecule and takes the value 0 otherwise. So, the total energy of the system can be written as a sum of four terms. The first is simply the addition of all binding energies, which is all we would have got in absence of interactions. The second term quantifies the interaction between any two given ligands, which are attached to the hemoglobin molecule. The third term gives the interaction between three ligands, and the fourth term gives interaction between all the four ligands when they are attached to the hemoglobin molecule. Knowing these energies, we can follow the same approach as was done for a single ligand receptor pair and calculate the weights associated with all the four macrostates of this given system. Knowing these weights, we can finally calculate the average occupancy, which is the average number of oxygen molecules attached to a given hemoglobin molecule. Now let us see how this model works for an actual system. This plot shows the binding of oxygen molecules to hemoglobin as a function of partial pressure or concentration of oxygen. The black points show actual experimental data, whereas the solid curve shows the fit obtained by using the model I discussed just now. The dashed curve shows the fit using a model which does not take into account the interaction energies. As you can see, the model with interaction energy provides an excellent fit to the given data. As seen from the plot, when the concentration of oxygen is very high, the oxygen molecules get bound to hemoglobin very efficiently. This is what happens in our lungs. As the hemoglobin molecule travels through the body and reaches places where concentration of oxygen is low, these oxygen molecules get dissociated from hemoglobin, providing supply of oxygen to places where it is needed. So here we have seen one example of how statistical mechanics can be applied to complex biological systems to give models which are simple but actually work. Thank you.
We hope you enjoyed today's program on the special occasion of National Science Day. At LIGO India, we celebrate science every day. If you're still not following our gravitational wave science blog, Gravity Matters, here's how you can do it. Let's take a guided tour of the LIGO India blog pages. So if you visit the LIGO India website at www.ligo-india.in, so at the end of the top panel, you will find the link to the blog pages. So if we click on it, we land on Gravity Matters page, which is a gravitational wave science blog from LIGO India. The first page has a description of the motivation behind why we created this gravitational wave science blog. To go to the pages, you can simply click on the Go to Blog button. So this takes you to a number of different topics which are accessible by buttons. First up, we have LIGO India Science. LIGO India Science is not only all about gravitational wave science, but also many different topics related to it, such as compact stars. So if you want to know all about neutron stars and black holes, if you want to know about the latest discoveries and events in the world of gravitational wave science written in a very lucid way, or about the theories of gravity, then don't hesitate to read the different blog articles which are contributed to gravitational wave students from all around the world. Next, we have a series of podcasts called Listening to the Cosmos. In these podcasts, the LIGO India team interviews famous international speakers from around the world who talk about their life and career and their particular contributions to the world of gravitational wave science. These interviews are also available on the SoundCloud LIGO India channel as well as on the LIGO India YouTube channel. Next, we have a section called Glorious Women in Astronomy. This section is dedicated to women who are contributing to the world of gravitational wave science. There are interviews of students, postdocs, faculty, and R&D scientists about the different challenges they have faced about their life and career. So this page is specifically meant to motivate all the girls who are thinking about a career in gravitational wave science. Storyboard section covers a wide range of miscellaneous topics, be it quantum gravity, be it articles written by gravitational wave scientists about how they got into this field, about books launched by students, about the history of gravity, and much, much more. We also have a new section called Polyglot, which is dedicated to gravitational wave science written in different vernacular languages of India. We also have GW SciArt, a virtual gallery for gravitational wave science inspired art. In this virtual gallery, you will find two sketches, posters, infographics, and much, much more, which is dedicated to gravitational wave science inspired art. Finally, we have a section called Behind the Scenes. In this section, students interview gravitational wave science students working in various different campuses around the world and interview them about their challenges, about their field of research, and much, much more. So the behind the scenes interviews are available on the LIGO-India YouTube channel. So do follow us on our blog pages, on social media, Facebook, Instagram, Twitter, and YouTube to find out all about the latest updates in gravitational wave science and life around it. The Gravitational Wave SciArt Theme Challenge is still on. Please send us your creative pursuits to get yourself featured on our virtual gallery. This is Debarati signing off from the virtual studios. Thank you very much for joining us today. Bye-bye.